Ladies and gentlemen, this is Alice. I'm so glad to meet you on this stage. This was iCANX Talks. This was a special program as iCANX Summit. So this is 3 days we here. Every evening we have a wonderful program. So this is Alice. Warm greetings from Beijing, and I hope all of you have a wonderful time with us. Today we have very good program. In the morning and in the afternoon, we have 8 sessions with a talk about different high tech. And this evening, we have 4 plenary speakers on the stage. So these 4 big names. Yeah, we'll come out one by one. First, let me introduce our first speakers. Professor Jean-Pierre Sauvage is Nobel Laureate and 2008. 16 and is from France, with University of Strasbourg. Here I have to adding emphasize just one sentence for Professor Jean-Pierre Sauvage, because he's so famous for a lot of things, and he's done many wonderful jobs. So here I have to announce one thing: is Professor Jean-Pierre Sauvage actually not only won once the Nobel Prize, should be twice, right? Yeah, because his work research and PhD that time already win Nobel Prize in 1987. I think as his supervisor, yeah. And what a lovely story is after 30 years, he win the Nobel Prize by another super work. So it's going to talk about this. So Professor Sauvage, stage is yours, please.
Thank you, Alice. So before I start, I would like to thank you very much for organizing this beautiful event. I had the pleasure of exchanging many emails with you, and those emails were always very friendly. So thank you so much. So the title of my lecture today is Topology and Molecular Machines, 2 interlinked research fields. And in a way, it will be some kind of a duet because I'm an old chap, and probably we were at the very beginning of these 2 fields many years ago. And David Leigh will, in a way, continue the lecture with this gorgeous and much more modern view on the field. So it's a real pleasure, to give a lecture just before him and to listen to his lecture. So just a few definitions. The definition is related to my field, of course, topology, which is the science of infinitely deformable objects. So I think no need to enter more into the details of the definition, but the only thing which you cannot do in topology without modifying the topological properties of the object you are working with is to cut things and to repaste things. In chemical topology, it is exactly the same. Using your mind, of course, we know it's not real, but you can pull on bonds and stretch bonds. You can completely distort angles. And this is not important in terms of molecular or chemical topology. Again, it's a vision of the mind. We all know that if you stretch a bond, at some stage it will break. Now, this field is related to knot theory. So knot theory is a very important branch of topology. And I just represented on this slide a few important prime knots. So we have limited time to discuss all the details of this theory. But you see that there are more and more complex knots here, starting from the trefoil knot, which is very famous in art and in many other fields of human activity. There is a beautiful knot here, which I'm sure Dave will talk about later on. And so the complexity of these knots is increasing. The first number 3 in this particular case, is the number of crossings, the minimum number of crossings you need if you want to embed these nuts in a two-dimensional space. Or in other words, if you want to project the nut on your sheet of paper, and you will observe at least 3 crossings for the spectral nut and many, many more for more complex nuts. And in terms of molecules, everything started long ago in 1961 with a paper published by 2 researchers, Frisch and Wasserman, Ed Wasserman, whom I met and who is still alive. And these people were working in a big company, namely Bell Telephone Laboratories. And I think it's interesting to observe that these 2 scientists were doing purely basic science. You know, they were not interested in applications. And that was allowed at the time by those big companies. And clearly, things have changed. And so Frisch and Wasserman noted that in topology or chemical topology, there are basically 2 main classes of molecules, those with a planar graph, like this one, a ring, you take a ring, and the ring, you can of course draw it very easily without crossings on your sheet of paper, and this is represented here. And they said that this molecule, if it's a macrocycle, let's say, has a planar graph because it has a trivial topology. Trivial meaning that you can represent it in a 2-dimensional space without crossings. And the other class of molecules would be the compounds whose molecular graph requires crossings if you want to represent them on your sheet of paper. And so these 2 classes are very important. In this case, you would say that the graph is non-planar, or in terms of topology, that the topology is non-trivial. These 2 classes are, of course, very, very different. But one should know that the molecules with a planar graph represent something like 99.999, a certain number of 9s after the point of the comma, % of the molecule. So there are very, very few non-trivial molecules in terms of topology. Now, let's look at what had been done in the past. And in particular, let's spend a few minutes on catenanes and rotaxanes. So catenanes are typically non-trivial molecules in terms of topology because you need 2 crossings if you want to project them in a 2-dimensional space. Rotaxanes are related to catenanes, but their topology is very different. It is trivial, unfortunately, for those poor rotaxanes. And chemists have been interested for decades, or more than a century, actually, in catenanes, trying to design simply by strategy, let's say, routes which would allow the synthesis of these molecules. But for many, many years, they were mostly objects for discussions. And I think that in the US, it was very fashionable to design projects on the making of catenanes for PhD students after their first PhD thesis. There are probably hundreds of second theses which were related to that. But very little happened till some extremely important work in terms of history of the field. Professor Gottfried Schill and his boss, Professor Arthur Lüttinghaus in Germany, in fact in Germany, but very, very close to my city, Strasbourg, something like 70 kilometers, could make a catenane. And I think that in 1964, when it was published, it was a big thing, a big event, and many chemists applauded. They were very impressed by this success. So they could demonstrate, I believe, unambiguously that they made a catalyst. There were already attempts in the past, but in my opinion, this is the first fully convincing piece of work which was published. The weak point, of course, was that it was a very long synthesis. There were 20 or 22 individual chemical steps to make the catenane, and clearly they could not obtain kilos of these molecules, but probably a few milligrams at most. And so this is the reason why chemists lost interest for the field. And for about 20 years, the field of catenanes was kind of dormant, and very little happened in this nice research field. So now I will switch and talk about our work and the way we entered the field of catenanes. So when I was an associate professor with my boss, Jean-Marie Leigh, in the 70s, we were very interested in a big project which was trying to split the water molecule to H2 and O2 using light energy, or more specifically, solar energy. And there were many, many people interested in this project, which is already true today, which is still true today. Many people are trying to split water to H2 and O2. And we had some success, but only partial. But at the time, I think the most important complex was ruthenium 3-bipyridine. Years, and he's still one of the heroes. Properties in terms of excited state lifetime, ability to transfer electrons or to transfer positive charges. And so everybody was working with ruthenium 3-bipyridine. But there is a big problem, because if you think of mass production of devices, let's say, ruthenium is not adapted at all. It's a noble metal, it is very expensive, very rare. And so some other metals have to be studied, investigated. And there were already some works by a few photochemists on ruthenium being replaced by copper. And if you can replace ruthenium for copper, it will be a big improvement, because all of a sudden you will use a metal which is very cheap, extremely accessible, and that would change completely the view we would have on inorganic photochemistry. And Dave McMillan was one of those pioneers, and we had contact because he knew the work we had done in Strasbourg, and he decided to spend his sabbatical leave in Strasbourg. And that was, of course, a great idea, both for him and for us. When he arrived in Strasbourg, from the very beginning, he decided that it would be nice to interact with us. And he visited our group, of course, and we had lots of discussions with him and within our group. And at the time, we had made a molecule which looked very simple, but which surprisingly was new at the time. It was the beginning of the 80s. And this molecule is diphenyl phenanthroline, something very simple. And when he saw the molecule, he was very excited because we didn't make the molecule for photochemistry, but rather for catalysis. And we had some success with iridium-based complexes and catalysis. But he said immediately, so you should make the copper complexes, which is represented here. And we will be very happy to do all the photophysics and all the photochemical studies. It should be a very interesting photosensitizer with a long-lived excited state. And this is what we did. And we had some success, indeed. It was an interesting complex, which to a large extent was able to replace ruthenium trace by pyridine. But probably the most exciting feature of the complex is what will follow. If you look at it carefully, you can materialize the two endpoints of this ligand. Let's call it the vertical ligand. If you materialize the two other endpoints of the horizontal ligand, so this one, let's call it the horizontal ligand, it's clear that you have a set of 4 points, 4 carbon atoms, and if you are able to interlink the 2 blue points and separately the 2 red dots here, you make a catenate. It's very simple. You make a ring containing the blue fragment, you make another ring containing the red fragment, and those 2 rings are interlocking forever. And we thought, well, that's an interesting observation, although we didn't know where it would lead us. And we decided to jump in a new field because, as I said before, the work of Schill and his co-workers was quite old, 20 years old. And we decided to try and make a catenane based on this very simple observation. So we had more or less to quit inorganic photochemistry, small molecule activation, and enter a new field. And we entered it thanks to the beautiful work of Christian Dietrich Buchecker, who was one of my best friends and a fantastic organic chemist. And she could make a catenane within a couple of months. And overall, it took us less than a year to have our first paper. And the title is in French here because we decided to publish in French. But it's, I think you can easily understand what it means, a new family of molecules, the metallocatenanes. No need to speak French to understand the title of this paper, I'm sure. And so that was the beginning of a new era for us. We became, let's say, people interested in catenanes, photoxanes, and molecular topology in general. So I will show you a more modern video because my students were not so happy about the slides I was using. You know, they said, you are using very old-fashioned and dusty slides, and so we will make something more attractive. And I hope you will find it more attractive. So we start from the molecule which is here, a very simple molecule, which you can make in 3 steps from phenanthroline. And now we will mix with copper 1, and we obtain this, which is what we call the entwined complex, corresponding to the entwining process. Now you can cyclize on the right, cyclize on the left. It's a one-part reaction anyway. And you obtain your catenane. And the other strategy, which is slightly more complex, is based on the synthesis of a precursor, a cyclic precursor, which is also obtained in 3 steps from phenanthroline. Now you will complex it with copper, and the second fragment will thread in, and finally you will cyclize. And both strategies have been used extensively by our group for making asymmetric catenanes, and you need the second strategy, the gathering and threading strategy, or symmetric catenane. So we could demethylate very easily, quantitatively, using potassium cyanide, and obtain the metal-free catenane, which is represented here, and remethylate quantitatively. Everything was done at room temperature. It's kind of instantaneous, so very, very easy. And we were lucky because we could obtain the X-ray structure of both forms, the copper 1 complex, which is highly compact and globular, And the metal-free species, which is much more open, which contains two rings, which can glide more or less freely within one another. That was really the beginning. Now let me pay homage to the people who had been working on catenanes and those who are also at the origin of the field, because for a few years, it's interesting, for a few years we had no competitor. We published the first paper in '83, and we had to wait for 6 years before Fraser Stoddart and some other people entered the field. And in a way, we were very happy to have competitors, because when you are alone as a group to work in a field, you really ask yourself, is it so boring, this field, or has it some interest? And we were happy. Fraser entered the field. And so here are the people who are really at the very beginning. Chris Hunter, Fritz Föckle, Fujita, who has done some fantastic work with palladium complexes, Dave Leigh, who published an extremely facile synthesis of the catenane in 1994, sorry, with an Angewandte Chemie cover page, very exciting. And so this is more or less the beginning of the field. And after that, many other research teams entered the field. I would like also to pay homage to Hiroshi Ogino, who is a Japanese scientist, still alive and still in good shape in Sendai at Tohoku University. And he published a nice paper on the making of rotaxanes using cyclodextrins as rings to be threaded, and then followed by stoppering of the system by attaching two big stoppers at the ends of the thread. So just to tell you that we were more interested in topology than molecular machines for many years, for almost 10 years. Molecular machines seem to be quite far away from our interest. And we devoted mostly our energy, our time to topology, molecular topology. So we could make more complex catenanes. That was not especially remarkable, but we were happy to do that. Probably the most challenging thing was trying to make a nut. And I will spend a bit of time, just a few minutes, on the making of the trefoil nut. And I know that David Leigh is with no doubt the champion of molecular nuts, and he will tell you about absolutely fantastic nuts, much more complex than ours, but we had to start somewhere, and so we started with the trefoil. So the trefoil nut is a part of art. You find it in graphical art, like Cornelis Escher, the Dutch artist, quite famous. And in Celtic art, you have nuts and interlaced design. And so we decided to try and apply a strategy which was related to the old strategy for making catenane. So this is what we have been discussed about the making of catenanes. Just to remind you, we take two fragments. Each fragment contains a coordinating unit somewhere here, let's say. We mix with copper, we obtain this species, we cyclize on both sides, we obtain the catenane, and we can easily remove the metal. So this is where we were when we started. And we thought, let's try to make it a little bit more complex, and we will use two fragments containing each a coordinating unit. So we connected those two fragments, very similar to that. And so this is what we obtained. And now we add copper, and if it works, as expected, or at least as hoped, we should obtain a double-stranded helix. We should be able to cyclize from here to here, separately to here, and then we would obtain a trefoil knot. Because this is already a trefoil knot. And remember, you can distort the molecules as you like, so this is equivalent to that, except that there are two metal centers here. So this is already a trefoil knot, and it should work. And we started in 1984, just after our first success here. And it took us 4 years before we succeeded. And so that was really depressing, but at the same time, it's a big joy, of course, the day you see your first knotted molecule. And so this is the work of Christian Dietrich Buchecker, as I said, a great organic chemist. She was sometimes a bit depressed, but she was recovering very fast, and she was extremely strong, psychologically very strong and determined. And so the first success came when we used a small fragment consisting of 4 methylene groups, CH2,4 here, as a linker between the 2 phenanthroline units. Now we add copper, and we obtain terrible mixture. So that was clear from the NMR studies. It was a terrible mixture of complexes, of copper complexes. And we knew that those complexes were kind of a dynamic mixture, and they would rearrange and exchange their structures with some other components. And so Christian decided to take the mixture as is and cyclize. And that was a great idea. And so she cyclized, and the molecules which agreed to be cyclized could be isolated relatively easily, and she obtained a trefoil knot with the respectable yield of 3%. Respectable and miserable, in a way, would apply. Miserable because 3% is not something you are so happy with, but it was the trefoil knot, and she could make 60 milligrams of it. And with 60 milligrams, basically you can do everything. You can characterize the molecule, so that was in the 90s or so, and do X-ray structures, NMR, basically everything. And so we celebrated, and even more after 1 year or so, we had an X-ray structure. And this is more or less, or I should say even exactly, what we had drawn. So that was drawn years before we obtained it. And it is very, very similar, as you can see. So we have the phenanthralines here, the 2 other phenanthralines here. This is the double helix. And the 2 coordinating fragments, which are polyoxyethylene fragments, are the 2 copper 1 center. So not a big surprise to see it, but of course a great pleasure, because it was a clear demonstration that the synthesis had been successful. Now, let me show you some interesting experiments we did, which show that knots are not totally useless in terms of chemical properties, and they showed something which was completely unexpected. So an accident, let's say. So we demethylated, of course, using tetraethyl ammonium cyanide, and the cyanide is avidly binding to the copper, and then copper 1 cyanide precipitates out, and the ligand was left without any metal. But a counter-ion here is very important. It is a totally innocent counter-ion which cannot interact with anything in this molecular structure. So we observed this species, we could isolate it. We were very disappointed because we could not obtain a nice NMR spectrum. It was an extremely broad spectrum, regardless of the temperature, And so we concluded that there was probably some slow snake-like rotation within the molecule, and it was a mixture of many, many conformers, so a bit disappointing. And then we did something else. We used potassium cyanide. And potassium cyanide led to something totally different. Potassium likes to interact with CH2, CH2O fragments, as you know, from the work on crown eaters and the many, many papers on crown eaters and cryptans. And so what we could show is that potassium was forcing the molecule to rearrange completely. The phenanthralines were pushed at the periphery of the molecule, outside, and the polyoxyethylene fragments or hexaethylene fragments were forced to occupy the inner part of the molecule so as to wrap themselves around two potassium ions, potassium cations. So we have a nice double helix here with the surrounding of each potassium ion being close to that in a crown eater complex, and the two phenanthralines were pushed away from the center of the molecule. And this kind of complete rearrangement, inversion in a way, is relatively unusual or even exceptional. So we start from a molecule which is slightly hydrophilic because of the hexaethylene glycol fragments at the periphery. And we remove the copper. We obtain another molecule, which is now completely lipophilic at the periphery. And this is reversible. You can do that as many times as you like. And we thought it's an interesting process, which, well, I like to talk about it nowadays, although at the time we were not so conscious of its interest. And now let me go on and talk about biology very, very briefly. At some stage, many people were telling us that probably we were doing completely useless research because catenanes and rotaxanes and nuts are not present in nature. They are useless in terms of potential applications. I'm not sure. Maybe they were right. I'm not sure. But catenanes and nuts are very common in nature. And this is what I use to answer those criticisms. And in particular, if you look at biology, you have lots of nuts, lots of catenanes in DNA with circular duplex DNA when it recombines or replicates. Proteins, and this is newer, you have to know that 1% of the proteins whose structure is in Cambridge databank, the big X-ray structure databank, 1% of the proteins are knotted. And viruses, I'm not sure there are so many viruses which are knotted, but one is a fantastic catenane. This is HK97, a bacteriophage virus, of course, totally innocent for mankind. And this virus, it has a normal shape for a virus. I mean, this is common in truncated icosahedron, or sphere, if you prefer, a distorted sphere. And the size is very normal to 60 angstroms or so. But if you look more carefully at the envelope of the virus, it is called the capsid, you observe that it's completely amazing. I mean, all the chemists, I think, working in the field were stunned to see a catenane. And so this is the capsid. And if you look carefully, you have a hexagon here, pentagon here, pentagon, hexagon, etc. So this is related to C60, because if you want to have some volume, a closed volume, you have to combine pentagons and hexagons. But here, in this particular case, it's a huge catenane, which is very similar to a natural chain mail. And the virus can distort itself so as to pass barriers and invade more easily bacteria. So that was very spectacular. And I'm sure that Dave Leigh and all the people who observed this structure more than 20 years ago were absolutely amazed. Now let's talk about molecular machines. And first, we will start with a statement. The statement is that synthetic molecules, most of the time, have been considered as static objects. It doesn't mean that they do not move at all. It doesn't mean that they are static, frozen, motionless. It means that they move in a random way, in a stochastic way, and that there are very, very few molecules whose motions can be controlled, simply. Although there are exceptions, a few exceptions. In biology, it is exactly the opposite. The most important biological systems undergo motion, and even much more important, controlled motion. Random has nothing to do with their motions. And so these motions are essential. And these systems, biological systems, are omnipresent in biology, in life. So I will just take two examples and discuss them very briefly. So there are rotary motors, linear motors, walkers, systems able to contract or elongate, etc. And these systems, these biological systems, belong to a family, most of them, the motor proteins, meaning that these proteins are very, very important, and they have to move and undergo some very well-controlled motion. So ATP synthase, at first, ATP synthase is a rotary motor, as probably many of you know. I think it is easy to say that this is the most important rotary motor on Earth, because everything which lives on Earth is based on ATP synthase or ATPase. ATP synthase, if ATPase makes ATP, and ATPase, if it hydrolyzes ATP to ADP. And you know that ADP and ATP are essential. ATP is really the fuel of life. And so ATP synthase has an importance which is beyond understanding. Some videos, you will find some beautiful videos on the web. Just one video also to tell you that things are very complicated. So this is the enzyme ATP synthase. It is embedded in a membrane, in the bilayer membrane of the mitochondria. The mitochondria are let's say, the energy factories in the cell, and it's a rotary motor. This part is the rotor, the central rotor, and the rest is more or less static. This is the stator, and this part here with an axis threaded through the cavity of this cluster of 6 proteins is the rotor. And it can rotate incredibly fast under artificial conditions. If you dope the system with a lot of ATP, it will try to do its best to hydrolyze as many molecules of ATP per second, and it can rotate at a speed which is really difficult to believe. They say 10,000 rounds per minute, which is really the Formula One of biology. So you see ATP in purple, which is produced, and ADP and inorganic phosphate being yellow and blue respectively. So fantastic system. And a video which I'm sure everybody has seen, more or less, which is due to some people at Harvard University. And it's a publicity for the kinesin. So the kinesin is an enzyme which is extremely important, which has several functions, but probably the most important function is in the cell, and all the cells, to carry molecules from one place to another. So some molecules are made in the cell using biosynthetic factories, and the molecules will be transported from one place to another place where the molecule is needed. And it can be hormones, it can be sugars, it can be small pieces of DNA or RNA, nucleotides. And you see here, you have a big sphere, which is the bag, the container, in a way. The people say the cargo. And so the cargo is driven by the kinesin, which is this little thing here, which walks. And I'm sure Leigh will talk about that much more in detail, because they were the first trying to reproduce this function. So what is so special about catenanes and rotaxanes in relation to molecular machines? Well, relatively obvious. If you take rotaxanes, so one rotaxane here, another one here, are catenanes, it is clear that rotaxanes and catenanes can be used for generating motion, and thus for making molecular machines. Here, you have a ring which will glide from the left part of the axis to the right part of the axis and go back to its original position. And this is very similar to a linear motion, like a piston moving in a cylinder, except that here it would be the axis which is fixed. Here you have some pirouetting motions, and I'm very careful not to use the word rotating machines. You have no rotating motion in this case, but in some cases it can be a fully rotating system, again, like maybe Dave will talk about. But most of those catenanes or rotaxanes are mostly let's say linear motors or pirouetting or oscillating machines, but not real rotary machines. So let me show you a very simple principle, which is the one we used already many years ago to set a molecular system in motion. Very simple. We will start from a catenane. And this catenane is slightly more complex than the one we have seen at the beginning of my lecture, because we have introduced here another fragment. It's a terpyridine. It contains 3 pyridine nuclei attached to one another. And so this is also called a tridentate chelating group. Tridentate because it can bind to a metal using the 3 nitrogen atoms which are here. Now let's think in terms of metal. Copper-1 is not a real transition metal, as you know. It's a D10 electronic configuration metal. So copper-1 is very happy when it is surrounded by a set of nitrogen atoms disposed in a tetrahedral fashion. So here you have a tetrahedron of nitrogen atoms, and this is exactly what makes copper-1 happy. Now let's perturb the system. So we send a perturbation, which is abstracting an electron from copper-1 to generate copper-2. So the right part is the copper-2 part. So we generate a copper-2, and the metal is still coordinated in a tetrahedral fashion. So the 4 nitrogen atoms are around the copper-2 center. But copper-2 is D9. It's a transition metal, of course. You have to take into account the d orbitals. And copper-2, because of ligand field, wants to be octahedral or 5 coordinated. And so in this particular case, copper-2 is highly frustrated, or another way to say it is that the complex, which is here, is very unstable. So the system will rearrange. The ring, which was originally like this, will undergo a 180 degrees motion, and you will now generate a very happy copper-2, which is 5 coordinated, which fits with its requirements, so to say. And if you want to go back, you can inject an electron, copper-2 to copper-1, and then the system will rearrange again so as to generate the starting form of the molecule again. Very simple. So a student of mine, Sylvestre Bonnet, who is now an associate professor in Leiden, in the Netherlands, decided to prepare something more modern for me, very kind of him. And so he made a video, which I hope you will like. We start from copper-1, we abstract an electron, generate copper-2. Copper-2 will be happy when it is 5 coordinated. We can re-inject an electron, we generate copper-1, etc. And just for you to know, the colors here are more or less the colors of the complexes. So it's a nice, colorful chemistry. You start from a deep brown, purple copper-1 complex. You oxidize, you generate a deep green complex. You wait for a bit of time, and you have a pale green complex, and you reduce it. You have, again, a deep brownish purple complex. So just to say that it works, of course, infinitely in my computer till it crashes, but it is exactly the same with the molecule. We have never seen any degradation. Now you may argue, is this a molecular machine? I would be tempted to say no, because you have only 2 forms in terms of geometry. But is it a molecular system which undergoes a large amplitude motion? I would say yes, with no doubt. So let me spend a minute on the fantastic work of Ben Feringa and his group. And Ben Feringa and his research team are located in Groningen, in the north of the Netherlands, which means very north. And they made the first line-driven molecular motor. I think it was a very important event in the field of molecular machines. And I will just discuss that very, very briefly. The drawings they used in their original work were not of very high quality, in my opinion. I hope he doesn't hear what I'm saying. But they were very difficult to understand for many people. And I think all that has been redrawn very rapidly by Credi, Balzani, and the people of the Bologna school in Italy. So you start from a double bond, and as you know, a sterically hindered double bond can be easily photoisomerized by shining light on it, UV light, not very harsh UV, but UV light. And so this is what happens here. And something which is really fantastic, I think they knew that they were doing this reaction, and they were mostly working on switches. But for some reason, they left the mixture stand overnight. And when the student came back in the morning, he did the workup, and they were very excited to notice that they didn't observe what they had expected. It was not that molecule, but it was rather this molecule. In other words, the motion, the rotary motion, went on, and they observed something which was more rotated, so to say, than what they had expected. So they were very excited. And then they continued, they decided to shine light. And I think Ben took the right decision. They irradiated again these fishes, and they observed that the motion was going on in the same direction. So that was the third form. And by heating a bit, they observed, they went back to the original state of the molecule. So they had discovered a rotary motor, a real rotary motor, and they are going at 360 degrees rotation, thanks to their, I think the way that they were very clever, very determined also to study all the details of this very important reaction. And that was, I should say, it paid, clearly it paid off. And so this is a beautiful video they published on the internet. I hope you can see it. So if I go back here, there is a photochemical process, and then a thermal step, a photochemical step, and finally the fourth step is the thermal step. So this is what is represented in the video. You have thermal steps. So this symbolizes heating, and two photochemical steps, which will be big flashes of light. Thermal, big flash, thermal, big flash, and we are back at the starting point. I still enjoy looking at it. I hope you can visualize the motion. I know it's not totally obvious, and I tested, many people, and some do visualize the motion easily, and some others have difficulties, but I cannot help those who have difficulties. Very sorry. So let's go back to our chemistry very briefly. So we started, as I said, in 1994. We published our first pirouetting catenane. It was very slow to move, and we spent probably close to 15 years trying to generalize the concept of using copper-1 and copper-2, or using ruthenium-2 and its excited state. We also made some molecular machines which are photochemically driven using ruthenium complexes. But it took us a lot of time to generalize and improve the system. And so just to tell you very briefly, so we made some pirouetting systems like that. And by modifying the structural factors of the molecules, we could convert the seconds to minutes of the very beginning to microseconds to milliseconds for the molecules we made in 2000, I don't know, 5, 6, 7, 10. But we have no time to talk about that. So now, let me pay homage to Fraser Stoddart and his group. And they were interested in molecular shuttles. A molecular shuttle is something relatively simple. So the ring can move from a position on the left to a position on the right, go back to the left. And the funny thing is that the first paper they published with two postdoctoral fellows, I think Bissell and Cordova, and Professor Ankel Kiefer, who was collaborating with Fraser Stoddart at the University of Miami. So that was published the same year as our pirouetting or swinging catalane. So that was good news for both of us. So again, relatively simple. They are using the blue box, which is a strongly electron deficient ring here. And this blue box can interact with organic electron donors like a diamine, an aromatic diamine, or an aromatic diether. And depending on the oxidation state of the green group here, the blue box can stand close to the green station when the green station is a good electron donor, or close to the red station once you have completely canceled the electron donating ability of the green station by making it a radical cation. And so that was really a very nice molecular machine. Some extensions, which I was very impressed with, as were many people. So they tried with Jim Heath, a physicist more than a chemist. They tried to make electronic memory devices based on molecules. So they could show that you can store information, you can process information using molecular systems combined to nano electrodes. So we have limited time for discussing that, but I believe.
JP?
Sorry?
Do you mind concluding? We are 55 minutes in.
Yeah, okay, I will.
Conclusion? Okay.
I thought I had an hour, so there was some misunderstanding.
Oh, sorry.
From, yeah.
Okay.
So I had less than an hour. Yeah? Okay, then I go straight to the conclusion. The conclusion is simply, very sorry for the misunderstanding. I just would like to say that what I spoke about is highly collective. And I would like to thank the group of people who worked with me, CNRS people, PhD students, and university professors. And there is a very long list. We have no time to talk about this long list. I'm very sorry for that. But if there is only one slide which should be kept, it should be these 3 slides. And finally, my university, my good friend from Maryland, Malcolm Green, who was a great organometallic chemist who passed away quite recently, very sadly, and you for your attention. Again, very sorry. I think there was some misunderstanding. I'm finished.
Okay, thank you very much, JP. My apologies for lashing you at that last minute. Very interesting talk. With that, I think we will switch to David Leigh. David is a Samuel Hall Professor of Chemistry and a Royal Society Research Professor in the Department of Chemistry, University of Manchester. And since 2018, he's also a distinguished professor at East China Normal University in Shanghai. He's one of the pioneers in this wonderful area, as JP mentioned. And I can't go through all the awards. He has many, many awards and many recognition. But I just want to highlight that his work is actually featured in this week's CNE news for having the highest number of notes on record. I think a recent paper in Science says about 138 or something like that. I saw the news brief. So let me hand it over to David and let him take over. Thank you.
Thank you very much, Martin. And a big thank you also to Alice for the really kind invitation to have me give a talk on this particular program. And in particular, it's a real honor for me to follow Jean-Pierre. It's great when you're in life, when your heroes become your friends, and then to also then be able to give a talk after them on related work. It's just a huge honor and great fun for me. So I'm going to continue talking about one aspect of what Jean-Pierre started this morning, or this morning UK time, and that is this one about molecular, this story of molecular knots. Oh, how can I continue? It's not, here we go. So Jean-Pierre introduced obviously topology fantastically, but knotting is about actually more than just pure topology, at least to us in my group. It's the chemical significance and physical significance of entanglements in molecules is related to the mechanical restrictions in strand positions and the restrictions in the dynamics about that. And as we'll see, that brings about consequences for molecular properties and opportunities that can bring about. And as we've heard already, in fact, biology does use knots in DNA, in proteins, in viruses. They occur in just randomly in polymers, and all kinds of physical manifestations of knotting are becoming apparent at the moment. However, of course, we use knots in the big world, and in the big world, we know that the topology of the knot, the precise nature of the entanglements, is really crucial for the knot's properties. So if you're hanging off a mountain on the end of a rope, you want to hope that that rope is held together either with stopper knots or hitch knots, and not with knots such as this slip knot at the bottom. That would be very sad indeed. And if that's true for the functions and properties of knots in the big world, it's likely to be true at the molecular level too. But unless we can make the different knots, we can't even begin to study them. And in fact, mathematicians have tabulated more than 6 billion different knot topologies to date, with less than 23 or so crossings. And all those knots topologies could potentially have different kinds of properties and different kinds of effects. But unless chemists can make them, or some of them, there's no way to either use or even to find out what those can be. And until recently, the only knot topology that had been made by chemists was actually the one that Jean-Pierre talked about, this fantastic trefoil knot that him and Christine made the first example of back in 1989. And in fact, for some 21 years, or 23 years actually, the trefoil knot, after the Strasbourg team had synthesized that, was still the only topology that had been made. There had been other examples that have been made through rational synthesis of trefoil knots, one by Fraser. Chris Hunter produced a beautiful example in 2010, and our group used our catalytic method of forming entangled structures to do so slightly afterwards. And trefoil knots had also been found as unexpected byproducts by Fritz Wertler and other groups. But in just a decade ago, in fact, the discovery of a trefoil knot in a molecular structure was worthy of publications in Science. And this paper by Jeremy Sanders's group pointed out the reasons why forming knots is just so difficult. In this paper, they discussed that the formation of knots requires very precisely defined pathways and transition states that are much more demanding to design than just simple macrocyclization reactions or just linking of molecular rings, formation of catenanes. And so, because chemists had only been able to design one type of knot, the topology, the trefoil knot, we decided to use the the skills that we developed in catenane and rotaxane synthesis to try and see if we could use that to make other kinds of knots. And the process that we use is really summed up on this slide. We come up with a basic kind of design, and then as so often happens in science, it's all about going to bottlenecks and solving problems. If everything worked exactly as you anticipated, you wouldn't really learn anything. And so science and synthetic chemistry turns out to be about problem solving, observing what you find. Sometimes you get lucky and you build on that, and you discover through this process new things which improves your understanding of in this case synthesis, and that allows you to design more complex systems. And I hope that you'll see how that develops in the field of knots throughout this talk. So Jean-Pierre discussed this fantastic realization that they'd had in the 1980s, that if you use the entanglement of the phenanthroline ligands around copper 1 cations, you could form linear helicates. And if you connect the ends of those groups together, A with B and X with Y in this case, you can form not just catenanes, but Trafor knots, Solomon links. But if you try and go higher with the linear helicates, this sort of approach becomes more difficult because it becomes harder to connect A with B and not with X or Y, at least with any kind of selectivity. And so this doesn't turn out to be a useful way of making higher order topologies. So we wondered, would it be possible to change from linear helicates, where you've got this long distance between the groups that need to be connected together, to form cyclic units, cyclic helicates, which would only require small connections between the end groups, and use those to try and form higher order molecular topologies. And again, in Strasbourg, there was a serendipitous discovery in the 1990s had given clues to how that might be possible, which Jean-Marie Leigh discovered that if you take these tris-BP ligand strands and assemble them with iron atoms to form these octahedral iron complexes, if you use different metal salts, you can form circular helicates of different size. So if you have chloride, it tends to template the assembly of pentameric circular helicates. And if you use other larger anions, you can form different sized helicates, such as this hexamer. And if you think about it, if you connect these end groups together, you could perhaps use that as the basis of forming cyclic topologies. However, there's problems in doing that. First of all, these conditions are very harsh, boiling ethylene glycol or very hot ethylene glycol. That's not going to be compatible with many chemical reactions that you can use for forming covalent bonds. And second, although this ChemDraw picture looks like these end groups are pointing close together, in reality, they're actually pointing in completely opposite directions. They point away from each other, and it's going to be very hard to twist these units round to actually cyclize. Furthermore, rather than just connecting the end groups of linear strands together, now we've got to connect simultaneously 10 end groups together in 5 reactions. So you've got to get multiple connecting reactions to assemble such a structure. And of course, if any one of those gives the wrong kind of connection or forms a byproduct, it would destroy the whole synthesis. So a way around that is that one needs to use reversible chemical reactions, so dynamic reversible covalent bond forming reactions, that and if those can be made to occur under thermodynamic control, those can perhaps correct errors that could form in the reactions and give you a thermodynamic product. And So we adapted these kind of ligand strands to suit that sort of purpose by changing the N-BIPI unit to be this pyridine aldehyde group, which can condense with an amine to form an imine bond to regenerate the chelating group of the terminal BIPI unit. And by doing that, by using imine bond formation, we were able to use milder solvents. This one's in DMSO, lower temperatures, 60 degrees instead of 160 degrees. And if we use a diamine with the correct structure, we can indeed cyclize all of these N groups simultaneously using these reversible imine bond forming conditions to form a pentafoil knot. Now, the structure of this linker turns out to be very important. If you replace these oxygen atoms for CH2 groups, then you don't get any knot forming. And that we'll see the reasons for that later. How do we know that we have the knot? Because we have an X-ray crystal structure. And if we start in the middle of this blue chain here, and we go around the actual loop, from left to right, you can see that the strand passes over the other strand, round the octahedral iron metal here, under the next strand, over the strand here, round another metal ion, under, over, round, under, over, round, under, over, around the final metal ion, under, and back to the start. So this is a single continuous loop. There's 160 atoms in the length of that loop. It has these 5 over-under crossings, and it's made from this 16 component assembly system. There are 5 dialdehyde building blocks, 5 diamines, 5 iron cations, and this chloride ion that templates the assembly of the pentamer in the center here. And if we rotate it round, you can see this lovely double helicate structure. And this chloride atom that templates the assembly is held in place by these 10 CH hydrogen bonds to the chloride ion that sits at the center here. And even though this is a very simple assembly process, that perhaps belies the complexity in the design process that we're seeing that's necessary to assemble this complex structure. So these metal templates are necessary for helicate formation, which creates within the circular helicate and in the linear helicate that Jean-Pierre showed earlier, all crossings of the same handiness so that it goes over, under, all the way round. The spacer between the chelating groups is crucial. Here we just have these 2 CH2 groups, and that gives rise to cyclic versus linear helicates, as Leigh had discovered serendipitously a few years earlier. The anion is important for templating the size of the helicate and therefore the number of crossings. Reversible imine bond formation allows error correction. So initially you form polymers, but over time, those intermolecular connections all go through to the thermodynamic product, which are intramolecular connections to form the knot. And finally, in the crystal structure, we can see the importance of why having these oxygen atoms are important. If these were CH2 groups, you would get these 1,3 diaxial steric clashes, which work to stop the turn required of this group, so it can turn back and connect the end groups of the building blocks. And so the gauche effect, the stereoelectron effects of these 2 oxygen atoms and the lack of the CH steric interactions are crucial for directing this ring closure. So we learn from the observations of what we've seen there, and it allows us to design even more complicated structures. So the iron atoms, if we just go back into the crystal structure again, you can see this is a double helicate, and these iron atoms actually bind to the strand at the outer by the outer groups twice in this kind of in the pentafoil knot motif. But we can also use the octahedral coordination of metal atoms to actually bind to 3 bidentate chelating groups and assemble 3 different strands and do a triple kind of braiding technique if we design our molecule correctly. And sure enough, if we take this kind of ligand strand, which is now terminated with alkene groups at the end here, so we can use ring closing olefin metathesis, as Jean-Pierre did to close some of his knots, then we can assemble this kind of circular helicate with this triple stranded helicate, close the end groups by olefin metathesis to again form a knot. Again, we have a crystal structure of this so-called 819 knot. It has 8 crossings now. And instead of being over under all the way round, we can see a different set of crossings in this molecule. So again, if we start in the middle of the crossing of this blue strand here and go around, you can see we go under now, round, then over this metal atom, over again, and then under, over as we go round, under, over, under, over, and back to the start. So this is 192 atom loop now. And these crossings, these 8 crossings are non-alternating. They go over, under, over the way round, all the way round. It's assembled in just 2 steps in 61% overall yield. And if we look at it rotate, you can actually see it's a very, very thin structure, this one. Again, with a chloride atom at the center templating the assembly. And this is actually the tightest knotted structure, physically knotted structure that's known in the universe. And for that reason, it appears in the Guinness Book of Records of the tightest knotted structure that's known. Another trick that we can play with trying to build on these sorts of topologies, besides changing the number of strands in the helicate, is to change the way that we connect the end groups of the building blocks together in the helicates to form different building block connections. And we can do that by using the conformational preference of the end groups here to restrict the degrees of freedom of the end groups and control the conformational space that they're actually able to access. And so in doing that, we bring the strand ends together so that this group is going to react with this one and this one with this one and the same all the way round. And what we can do with that sort of system is that when we close the end groups, then we get an even larger structure. And this is a 9 crossing molecular knot of these sort of 3 trefoil knots that are all connected together to form a single loop that contains these 3 trefoil tangles all in one great big loop. I'm not going to do the over under tracing round, otherwise we'll be here all afternoon, because this is a 324 atom. 324 atoms are in the smallest loop that you can trace around this backbone. These are alternating crossings again, so over under, just as you would see in a normal trefoil knot. And it's prepared with complete stereoselectivity in 65% overall yield in just these 2 steps. And just to put the size of this backbone in some sort of comparison, this is the same length as a 108 residue peptide, but it forms a single large macrocyclic structure, which has this additional complexity of having 9 alternating crossings all the way round. This is the crystal structure of that molecule. That's how we know all the connections are right. And now you can see, compared to the 819 knot that we saw before, this is a much more 3-dimensional and larger sort of volume of structure, reflecting this the size of this enormous macrocyclic loop with these crossings. Now, a effects of that you can get with these knots are also quite dramatic. So chloride, if you remember, is used to template the assembly of some of these knots, and the chloride is held in place extremely tightly in these knots by the CH bonds of the pyridine that are connected to the ion that sucks the electron density out. And this makes this knotted cavity an extremely strong binder to chloride. In fact, it's one of the strongest binders of halide ions that's known. And the binding is so strong that if you pull the chloride ion out from the center of these knotted molecules with, for example, silver salts, then the empty knot will sequester chloride ion from the solvent or the glassware that you keep the knot in, unless you keep it in the presence of silver salts. So it's extremely powerful binding of chloride ions. And you can use that binding to actually do interesting things, such as to do catalysis. So if you take the knotted ligand after you pulled out the metal ions, then you can treat it with metal ions such as zinc. The zinc molecules will bind to the biphenyl group, the BIPI groups that are in the strand. Those will bind to the zinc ions to regenerate this chloride binding pocket or halide binding pocket. But if you've used zinc ions that are BF4 salts, they won't go into the pocket, they're too big. And so this cavity is present that is extremely halophilic. And you can use it to pull the bromide ions off this trityl cation, this trityl bromide, to generate the trityl cation that you can then use as a Lewis acid to do catalysis, such as Diels-Alder and Michael addition, could catalyze those kinds of reactions. That puts the bromide or halide back into the cavity. It can then be removed to regenerate the ligand, and you can go round in this kind of cycle. And it's only having a knotted strand that allows you to do this. This is showing the sort of importance that the restrictions of conformations that knots allow you to do, how they can be useful. If you try to do this with a linear strand, it'll just form linear helicates, and you won't be able to form these high energy conformations with high energy binding sites in the center of them. So linear strands or non-knotted strands can adopt lower energy conformations when they bind to these metal ions than the knotted strands do. And this is sort of a use of topology that can be used to generate effects that you can't do without knotting these kinds of ligand strands. This is another kind of application that you can use these structures for. You can use them, these kinds of knots, in membrane binding to allow them to transfer anions in and out of the center of vesicles. And you can use these kinds of units in other ways as well. We can use other binding motifs. We don't just have to use circular helicates. If you take lutetium lanthanide anions, then those are able to assemble these kinds of pyridine dicarboxamide units around the metal ions and hold these end groups in a particular arrangement so that you can close them to form trefoil knots. And if you use chiral groups on the ligand strands here, you can actually use them to form trefoil knots of only one handedness. So the point chirality in these kinds of lanthanide binding units allows you to form trefoil knots of only one topological chirality. And having molecules that will bind here with groups that will be selected to bind to lanthanides is exciting, because we can actually combine those with the kinds of phenanthroline ligands that Jean-Pierre's group pioneered to bind to transition metal ions to form knots. We can combine these two different kinds of orthogonal binding modes these kinds of units that want to bind to lanthanide ions, and the phenanthroline units to bind to the copper ions, and get them to do kind of more than just the sum of their parts. So if you take this ligand strand that you can build and just connect the end groups together by metathesis with no metal ions presence, you just form a macrocycle, a so-called unknot with no entanglements in it. If you just expose this ligand strand to lanthanide ions, then just as I showed on the previous slide, these will assemble to form a trephine knot. But if you combine them with add copper ions and lutetium ions, lanthanide ions, then you can do something else. First of all, if you add copper ions, you can form a loop between the two phenanthroline units here. And then once you form that loop, the lanthanide templating groups, if you add a lutetium ion, can thread through the center here. And if you close the units here, you get a new kind of knot, a so-called molecular 3-twist knot or a 5-2 knot. And here's a video short of showing this process. So this is adding copper ions, which, as Jean-Pierre showed, can form these beautiful axially chiral, actually, chelate groups with the tetrahedral metals. And once that's formed, the lanthanide groups can, lanthanide binding units can thread through the loop that's made to close the ends. And you actually end up with a new kind of knot that has got 5 crossing points. And it's different to the original pentafoil knot. This is a 5-2 knot. It's got a different sequence of over-under crossings to the pentafoil knot. And so this is kind of a way of being able to assemble units together by controlling in a single strand, just by controlling the different ways of forming entanglements. And again, when you do this kind of work, you often discover new kinds of things unexpectedly. So when we made the lutetium templated knot from this process, the student who was preparing it put it down a chromatography column that had previously been used to purify something that contained copper 1 ions. And when the molecule came out at the other end, the NMR spectra of the knot was completely different to the knot, the knotted complex, when it had gone on to the column. And in fact, what had happened was that the knot had sequestered copper 1 ions from the chromatography column. Those had displaced the lutetium ions, and we'd form a new kind of complex. So what happens here is that the copper binding is stronger than the lutetium binding, and it twists the conformation of the knot, as Jean-Pierre found with when he demethylated his copper 1 knots and added them to metal ions. Here you get a large amplitude change, and in this case, you actually change the number of crossings that are present. This knot in this conformation has 4 crossings. So we say it has a writhe of 4 compared to the traditional writhe of 3 that you see with the other knots. And our most recent work on this area has been to make even larger knots by using this principle of Vernier templating, which was introduced originally by Ross Kelly in the 1980s to make linear duplexes of precise length. But about 10 years ago, Harry Anderson used this approach for making very large but topologically trivial macrocycles. And what Vernier templating relies upon is a mismatch in the number of binding sites, complementary binding sites on components. So if you have a component that has got 6 binding sites on one unit and 4 on another, it will assemble to form the lowest common multiple of binding sites. So in this case, you would have 3 of the 4 binding site units and 2 of the 6 binding units to form this kind of complex. And if you can connect those 2 groups, those different groups together around the template, you can form this very large macrocycle. So we wondered if you could take this Vernier templating route one step further and use it for the constructions of knots, not just controlling assembly size, but also using it to control strand entanglement. So another degree of complexity. So this is the system that the lanthanide templating system that I mentioned a few moments ago, where we have these pyridine dicarboxamide sites that combine to a single lanthanide unit in a strand to form a one-to-one complex. If you close that, you'll form a trefoil knot. But if we mismatch the number of binding sites in the strand, so we only have two of these pyridine carboxamide units with the tridentate lanthanide unit, then we can force three of these strands to assemble around two of the metal ions, and we can actually stereoselectively form a granny knot. And even more demandingly, I guess, if you have four of these units to bind to one of these metal ions, you can form this huge 3 to 4 stoichiometry complex, which is sort of a trefoil of trefoil knots, and close that to give a really large knot. And this really works. So this is a strand that contains four of these tridentate binding sites that will bind to a lanthanide ion such as lutetium in the ratio of 3 of those strands to 4 metal ions. So we form these trefoil tangles on the outside, and with the leftover component of the strand, those all assemble in the center around another metal ion to form these beautiful Celtic type of knots. And if we just close these by ring olefin metathesis, those can be closed to give these 12 crossing knots, which are 378 atoms long in the chain. This sort of so-called trifoil of trefoil knots. And we can actually introduce another element of into the design of these structures. If we change the chirality of just one of the end groups of that knot, then this chirality is mismatched with the other chiral groups on the strand here and won't be able to form coordination complexes with it. So this chirality of the strand is left over in the center here, and so the chirality of the topology or the entanglement that's formed by this central unit is different to the chirality of the trefoil entanglements around the outside. And so if you close the end groups there by olefin metathesis with this kind of ligand strand, you actually get an isomer of the other knot. It's exactly the same size. It's a 378 atom long strand. It has the same number of crossings. It still has 12 crossings, but they're not all alternating now. Now they've got 6 alternating and 6 non-alternating crossings around this loop. So this actually goes under, over, under, over, under, over, under, over, okay, all the way around. So we call this an inverted core trefoil of trefoil knots. And this knot and its isomer, the triskelion knot that we saw before, they have different properties. They're isomers, but they have different CD spectra because of the different topological chirality. And they also have different properties such as their actual size in terms of Dozy experiments and so on, and so flexibility of conformation. Okay, just very quickly, I'm going to tell you about some other kinds of topologies that we can make. The circular helicate route is great. It's very versatile, but it only allows you to make certain kinds of knots. They're so-called torus knots, so knots that will be able to be wrapped around a torus. And other topologies can't be made by those sorts of routes, and yet would be lovely to be able to make. And a few years ago, we decided to try and make this kind of topology, which has 7 crossings plus these 2 so-called nugatory, that means fake crossings at the end here, which we realized that we should be able to make from an interwoven grid. And this was appealing to us because it's a very kind of important classical knot, and it's the simplest form of simplest type of Chinese knot. So this is great. We realized that we should be able to make it from an interwoven grid. The problem is that 3x3 interwoven grids are unknown in the chemical literature, or they were when we started this work. And the reason is that when you try and entwine and thread together ligands to try and push them into a grid, you're going to get, if they're going to coordinate to metal ions, you're going to create stress on these units. This same sort of stress that you can use to assemble sticks together and get them to hold together, but at the molecular level, introducing stress into molecular structures is going to disfavor their assembly. So if you're going to try and make something like this, you're going to need something where all the metal ions can assemble perfectly in plane. So it can't be something like this where the metal ions won't be able to line up. That would create too much stress. And we identified a few years ago that this kind of ligand strand based on a so-called TTZ motif should be able to hold metal ions, according to molecular modeling, in a perfectly linear array. And we did this just in a 2x2 grid, and you can see in the X-ray crystal structure of the Solomon link that's made from this, that these metal ions really are all in the same plane. So all that augured well for trying to design this interwoven grid. And so the strategy that we tried to use was just to sort of extend the ligand, this kind of motif that we'd used for the 2x2 link to this 3x3 one. And then it's a matter of trying to play with these ligand units to try and optimize the chain lengths for making the closures and the electronics of the ligands to promote assembly. But when we tried to do these, we would make the strands, we would treat them with zinc salts such as zinc triflate, and we wouldn't get any assembly of any grids that we wanted. So as what happens in these processes is we go back to this sort of design, problem solving, observation technique, change the ligand strands, change the design, add more electron donating groups, change to try and bulk up the coordinating ability of these molecules, try again with zinc triflate. Nothing is being formed that corresponds to the grid here. But at this moment, the postdoctoral worker, very talented Jean-Francois Lemonnier, who was doing this work, recalled that the X-ray crystal structure that I showed you just earlier of the zinc-Solomon link of this 2x2 unit, we'd done that with BF salts. And he remembered that we had BF4 ions are actually in the center of the cavities within that crystal structure. So this was an observation that the postdoc did. And so we switched. We've been using zinc triflate before and getting nothing. And so Jean-Francois switched from using zinc triflate to zinc BF4. And when he did that instantly, within 2 minutes, the ligand strands assemble to quantitatively give you this 3x3 interwoven grid. How do we know that's right? Well, here's the X-ray crystal structure of that grid. It's not actually the one of the not these. The end groups are connected together here mathematically, but this is the X-ray crystal structure of the grid. And you can see that these four BF4 groups are actually crucial for the assembly, and you can see why. Here they're stabilizing the structure that is present in this knot. And if we rotate it round, I hope you can see that all the metal ions are perfectly in one plane. And this really is this beautiful 7-4 Chinese knot that has been made. Okay, finally, knotting is actually very close to weaving in terms of techniques that we use in the big world, macroscopic world. They're both achieved by controlling the crossings of strands at particular points with stereo control over under crossings. And just a few years or a decade after Jean-Pierre's group introduced the idea of making knots and catenanes and rotaxanes using this metal templating, Darrell Bush, who was actually the father of template synthesis in the early 60s, wrote an account of this area, talking about the potential of the ideas that Jean-Pierre had introduced, saying it's hard to know what the new ingenious new template type divides by Sauvage and associates are going to do. It remains unclear their significance, but he said it's intriguing to reflect on the possibilities of producing highly ordered entanglements. And a little bit later, Bush wrote another review saying the ultra aspirations of chemists working on interlocked structures might be to weave molecules as though they were macroscopic threads, coming up with these kinds of designs. But for 30 years, these kinds of structures were impossible to do. But the X-ray crystal structure that I just showed you of this 3x3 grid, this is the actual crystal structure of that grid. And it actually forms layers of these 3x3 grids, which are separated by anions between the layers. And within the layers, these N groups that are all together, you can see that if you connect them together across the cavity here, you would actually form a woven structure. In fact, even if they don't connect in the right way, even if this one connects here, the strands are still woven. They just wouldn't all be linear. So as long as you connect all the strands within a layer, you'll end up with a woven kind of material. So we decided to try that. We changed the double bonds at the end here for thiols, because thiols can be connected together to form disulfide bridges in the solid state by just air oxidation. So we took this material, formed the 3x3 interwoven grid, and then just allowed it to precipitate or crystallize on the surface, exposed to oxygen, so that we formed disulfide bridges. We then obtained a material that we could demethylate with potassium cyanide to form a wholly organic material at the end that contains no metal ions. So this is the assembly process shown here. This is the ligand for with the 3 TTZ groups. We add the copper one, in this case it's zinc ions to this, sorry, to form these structures with the BF4 groups, of course, so that they'll form the 3x3 interwoven group. We've got thiol groups on the end. This precipitates or crystallizes on the surface, and we form disulfide linkages through air oxidation. So this joins the strands, sometimes with errors, but all of these are forming connections just within the same strand. We then take that material with the, which we presume to have the, if it's like the crystal structure, to have these metal ions. We demethylate it. This will strip out the metal ions and the anions between them to leave this fully organic material. And if we pull out from that, AFM and micrographs of that show that this actual material is extremely flat. So if you do AFM on that material, you just see 4 nanometer jumps, nothing else across the whole of this strip. Everything is in layers. And this is because if you drag the AFM across the top here, it's just bumping down whenever there's a fracture in a layer. So there's no interlayer polymerization in these cases. These are either bilayers or monolayers that are that go flat across the whole of the material. There's no polymerization between the layers because of those anions that were present when the disulfide bond was coming. Again, if you look at it, you can see wrinkles, which is like you see in graphene, where the material wrinkles up. This is just a single layer thick of that material. So this is like the Turin shroud. And if you go across here, just one layer of this polymeric material, you can see where it dips down into the surface, always these just 4 nanometer dips. This is the finest woven fabric that's known. It's got a thread count of between 40-60 million strands per inch. And so that's also in the Guinness World Records as the finest molecular, finest woven fabric. If you pull on this material, it fractures in straight lines, just like a fabric, and it delaminates as you pull it, just as you would if you stack carpets along each other. So again, if we look at an image of that, if you put this on a material and pull stress across it, it'll break in straight lines, in fracture, just like a macroscopic material. And if you pull the strands apart, the layers apart, they just move across there. This material has different properties to the unwoven material, and if you press into just a one-dimensional polymer that's unknotted, you can push down, but this is like a net that retracts just like a woven fabric does. And so it's got much finer mechanical properties than you would find in a normal material. I see I've used up too much of my time. So you can also use this actually as a net for actually sorting out anions, but I shall gloss over that for now and end by saying, so where have we been able to take this wonderful field started by Jean-Pierre's group? Well, these are now materials that are realistic properties for synthesis. Their knotted structures are abundant in nature, as we've heard earlier. There's got to be reasons for that. And the consequences of orderly entanglements or properties can now be investigated. Introducing knotting and weaving revolutionized prehistoric topology technologies that allowed prehistoric humans to clothe themselves, to come out of caves, to make weapons, to kill, capture fish and animals. Can nanoscale knotting and weaving have a similar effect on technology? I don't know, but hopefully these are the people who in the future will be able to investigate those kinds of problems. I'd like to thank my group for all their wonderful creativity, imagination, and hard work. And thank you all for giving me the chance to talk to you today. Thanks.
David, thank you so much. Extremely, extremely fascinating talk. And it's a great pleasure that you are able to entertain all of us with such wonderful work. We do have about 10 minutes to jump into a panel discussion. And JP, Dave, my apologies, time was a little bit short on us, but you know, whenever there's good science, you never have enough time to discuss this. And I wish we had more time. So to get us started, I really admire the way you both have given the perspective on the field. And with every field that is doing something so drastic, so great, you always have this question of what next? So for the young investigators, for the students who are coming up, where do you see this coming up? Or where do you see this going? Who should be jumping into the field besides the supramolecular chemists?
Well, I think that sometimes science moves slowly in order to generate the initial ideas. But you can see how fast it actually moves once the first steps has been made. And today's two talks just showed that. I mean, Jean-Pierre work established what were the ideas. Who could have conceived that to make topologies to try and tie knots with metal ions? But once that is done, it sets the groundwork for then others to be able to then learn what the rules are, to pick up the ball and take those. And now even molecular weaving is possible, something that couldn't have been imagined when not so long ago. And I think the chance for the next generation to come along, the challenge for them will be to be able to make these to find out what these properties are that you can do with them, and do them ever more simply so that their properties can be exploited.
JP, any comments?
Maybe.
Yep.
May I?
Yep.
Yeah.
Okay.
Well, this is something that Dave already knows. I'm an absolute fan of his chemistry, no doubt. And what they have been doing with his group is really incredible. You know, honestly, 20 or 30 years ago, when we were doing our chemistry modestly, and I think we would never have thought that somebody else, you know, a bit later, 20 years later or so, would come up with such incredible discoveries. I mean, the topologies, you know, that Dave has made with his group, again, this is something, to me, you know, it looks marvelous in the sense that it's unbelievable. You know, it's like a fairy tale. Just a quick reflection on science. I'm sure we will all agree. Science is a continuum. You know, you cannot isolate, you know, some people who are really creating a new field. You know, there are some people who contribute than others. Okay, of course, I do not argue on that, but it's a continuum. And so when we see what Dave has done, you know, he's one of the most visible scientists in the world, but him and myself too, we also owe a lot to ancient chemists, let's say ancient times. And so this is why I say, you know, it's a big stream, and there is a boat from time to time, you know, which is more shiny than others, and that's all.
Yeah. Very good.
Martin, can I jump in on some questions? Yeah. So as Jean-Pierre just say that you have, you know, work with others, yeah, right? It's like a group, you talk with others, get inspired with others. I'm wondering what environment in Strasbourg. So it come out so many, you know, great works and great peoples. So is there a group, you know, very kind of mixed with chemistry, physics, or someone? You know, in Strasbourg.
Could you ask your question more specifically, if you don't mind?
Yeah. Okay. So sorry. I mean, in Strasbourg, you know, you together with Professor Leigh and also many other, you know, professors. Yeah. Are they all chemistry? Are they okay from a different field working together?
Yeah, it was. I mean, working with Professor Leigh was very challenging in the sense that you know, you have some kind of model that you would like to reach, but you know that it's impossible. And but at the same time, it was very very motivating. And I think I would never have reached, you know, the Nobel Prize level if I had not met Jean-Marie Leigh at a very early stage in my career, no doubt. And this is one of the joys in this business, so to say, in this field of research. You meet very exciting people. You know, some of them are older and more experienced than yourself, and you meet also younger people like Dave, you know, whom I know since he was a PhD student. I don't remember which year, Dave, 80 something. 84, perhaps.
Yeah, 84. 84, you
84.
visited Sheffield. One of your first lectures, I remember, that you said on catenates. Yeah.
Yeah,
and
right.
I was in the
when
audience.
You were a long-haired guy, and yeah, right. And so you meet young people like that, and this is also very motivating. So you are pushed by the senior people, but also by the younger people, and it's a joy, you know, to be in the middle of all that.
Okay, great. Yeah. So Martin, please.
Okay, JP, coming back to you, you know, it's very easy for people who are way much early in their career, like me, to start dreaming of starting new fields. But the problem you always feel is loneliness. I mean, scientific loneliness. You're not sure whether this will work, it's risky, and sometimes you even doubt your own knowledge, right? And the question that you always wonder is, who cares? It's driven by publication, that if you cannot get it accepted in good journals and the reviewers come back really hard, it becomes really demoralizing. So seeing what you did, you know, starting something like this that others can build on, what would you encourage young people to do in this very publication-driven media environment and very metric-based environment? How is it to start a field and even push? And I think, Dave, you can also comment, because all this meeting stuff you're doing is beautiful, but it's risky. So what would a young person think about when they're starting up something completely new?
You know, you have what the Americans used to call bread and butter. You know, you have a part of your research project which are relatively easy and which will be successful, very likely successful, and the other part which is more risky. And that was more or less our strategy, you know, to have, let's say, some kind of minimum production of publications, and at the same time, very risky projects for professional people. And this is the good, you know, the good system in France. You know, we complain, everybody complains all the time about our research, which is not good, which is true, and the system, which is not good, which is partly true. But at least we have something nice, which is that we can work as a group of permanent people. You know, and I have always worked with 5 or 6 permanent people, some of them of my generation, who didn't want to become a boss, you know, and take risks so much. But these people, they don't care if they have no data for a year or 2, you know. I shouldn't say they don't care, but at least it's not too serious for them. And in the UK, I think it is very different. You have to be productive. You have to publish lots of nice papers in the very fancy journals, it seems to me. But Dave is so successful that he's not going to complain about the British.
No, I could complain a lot about lots of things, but I agree that those are first world problems. But what I want to say is what's actually important is the output, and what you, which doesn't mean what journal you published in, it means what you discovered and what you brought to a field. And you saw a perfect example of that today, that Jean-Pierre published the first catenane in tetrahedron letters in 1983 in French. And that was work that eventually led on to a Nobel Prize. And so it doesn't matter where you publish. It's what I mean is, in terms of it can matter for metrics in this metrics-driven system that we're in. But at the end of the day, what is important is what you discovered and what you brought to the world.
I totally agree. You know, that was also my boss, Jean-Marie Leigh, who used to say, well, we can publish basically in any journal. If it's good chemistry, good science, it will be seen by all the people.
Yeah.
Maybe it will make a difference in the, you know, the time before they see the work, or it will be 6 months or a year later if you publish in tetrahedron letters than if you publish in JAX or whatever. I fully agree with Dave. I fully agree.
Alice?
Yes, I think this also can echo here. I remember one Japanese, a scientist, he published his paper on a Japanese, journal. Maybe no one knows, but later, 30 or 40 years later, he won a Nobel Prize. I think that's very important to answer the questions from the young generations here. From Fudan, he says that why the people, go to the fundamental science. I think that's the reason. You go to fundamental science, you found the why, and you found, what is important. So all this doesn't matter with where you publish, and you get a known or not. But it's the problem you solved. Yeah, that's very important. I think today we met, models here. Yeah, thank you.
Fantastic.
Okay, Martin, I think almost the time we need more. Okay, yeah.
Thank you,
Sorry,
JP.
time is
Thank you,
not,
Dave.
it's always limited. Yeah.
Right.
Okay, thanks,
Alice.
Professor P and David. Yeah, thank you so much
Thank
for
you.
wonderful, examples and so many, interesting stories here. And today we really have a happy, schedule. So we will move on, and we hope to see you next time. Okay, yeah.
Thank you.
Okay, so yeah, we
you.
move on
Bye.
to yeah.
Thank
Our
you.
next session, yeah, it's Professor Xi Peng already here. Okay, Peng, please, introduce Professor Hill.
Okay, hello everyone. Thank you, Alice, for your invitation. It is my greatest honor to chair the following two talks given by the two renowned founders and pioneers in the field of biomedical optics. My name is Peng Xi. I'm from the College of Future Technology, Peking University. Our first speaker is Professor Stefan Hell. He is credited with having conceived, validated, and applied the first viable concept for breaking the abyss diffraction limited super resolution barrier in the optical microscope, hence the born of super resolution microscopy techniques. He is the laureate of both the 2014 Kavli Prize in Nanoscience and the 2014 Nobel Prize in Chemistry. The title of his speech today is MINFLUX and MINSTED, provide molecular scale resolution in fluorescence microscopy. Now, let's join me to welcome Professor Stefan Hell.
Hello everyone. I'm going to talk about MINFLUX, which I think is one of the most exciting developments that are taking place now in fluorescence microscopy. To be very precise, in super resolution fluorescence microscopy or nanoscopy. And MINFLUX is so important because it's a game changer. It's a game changer in the way individual molecules are localized, and therefore also a game changer in the way molecules are separated at very, very small distances. Now, in order to explain to you how MINFLUX works, I'm going to talk briefly about the basic principles of standard localization, so the standard way of finding the position of individual molecules. Now, people have localized individual molecules for ages, to be precise, for about 4 or 5 decades. And during these 4 or 5 decades, they kind of thought of localization as a method by which you illuminate the fluorescent or the focal plane of a fluorescent microscope, and then watch actually or scrutinize the diffraction pattern of the fluorophore that is produced on a camera. A camera is nothing but a pixelated detector, and of course the fluorescence that is produced by an individual molecule is diffracted because the fluorescent light propagates as a wave, and therefore we get a diffraction blob of light on the camera. Now, this blob of diffraction light has, of course, a centroid, and this centroid must correlate in space with the actual position of the molecule. So by calculating the position of the centroid of the fluorescent molecule on the camera, we know through geometric optics, so to speak, where the molecule is actually located within the image, and therefore also within the sample space. Now, localizing a molecule by calculating the centroid of its fluorescence diffraction pattern on a camera is very greedy in terms of fluorescent photons, because the precision that you get depends on the inverse of the square root of the number of detected fluorescent photons. square root of the number of detected fluorescent photons. That means that you need many, many fluorescent photons in order to get the precision down to very small numbers. And the fact that there is a square root dependence makes matters worse. And therefore, this way of localizing individual molecules has serious downsides. And the downsides are that fluorescent molecules bleach, so it's very hard to get high numbers of fluorescent detections. And then if you get them, of course, you have to wait for a long period of time because it takes time in order to get many detected photons. And there is another problem that comes in that is due to the physics of the fluorescence emission. Fluorophores have a so-called emission dipole, and of course the orientation of this emission dipole plays an important role for the actual position of the pattern on the camera. So it can be shifted around if the orientation is not favorable. And therefore, this way of localizing molecules, though it is very simple and has been ubiquitously used in fluorescence microscopy, in concept of single molecule localization microscopy, in the tracking of individual molecules, is definitely not the best way of doing it. I'm going to explain to you why it's not the best. Why? Because there's another way of localizing molecules which is based on a very, very powerful principle. You see, if you do an epifluorescence illumination, the illumination photons do not carry any information. They are just uniformly spread across the focal plane. But if you use a beam of light that carries position information, like a donut beam, then of course you can take that piece of information in order to find out where the molecule is. And I'm going to be a bit more concrete now. If you have a laser beam, for example, that is converted into a donut, the donut zero very nicely, very precisely defines a coordinate in sample space. And so the photons that come from the laser, the excitation photons, excitation beam photons that come from a laser, very clearly define a position in sample space. And now, if you want to localize the molecule, that little star that you see right next to the center of the donut, the only thing we have to do is we have to find out how far that little molecule is away from the position of the donut. And the position of the donut is very well known, because in this scheme that we call now a MINFLUX scheme for localization, we can position actually the donut in the sample plane, basically to any position in the sample plane. So if the donut is, of course, coinciding with the position of the molecule, there will be no fluorescence emission because the donut excitation beam has a zero in its center, so there will be no fluorescence emission. And if it's, of course, away, then there will be fluorescence emission. So in other words, we can find out how far the molecule is away from the donut zero just by measuring the brightness of the fluorescence emission, the fluorescent rate. And although we don't know where the molecule is in the first place, of course, we can find that you can get a distance information from the brightness of the fluorescence emission. So if the molecule is only slightly away from the position, the fluorescence will not as bright as in the previous case. Now, in order to explain to you why this scheme of injecting a position with an excitation beam saves fluorescent photons, I've explored a little thought experiment. So since my last name is Hell, I thought that I would have to introduce a demon. And this demon, of course, knows something that we humans don't know. And in this particular case, the demon knows where the molecule is. And let's assume for a moment the molecule starts moving. What will happen? The molecule moves around, and the demon, knowing actually where the molecule is, shifts the donut, or the donut zero, if you will, around in such a way that the zero always coincides in sample space with the position of the molecule. In that case, of course, the demon can always trace the position of the molecule. It can track the position of the molecule with arbitrary precision because it is identical with the position of the donut, and the position of the donut is controlled by the demon, of course, by the little beam deflector that is shifted around by the demon. Now, this little thought experiment tells us something very important. Of course, there is no fluorescence emission when the zero coincides with with the molecule, and therefore we can get an arbitrary localization precision without any fluorescence emission. And this must now be contrasted with the previous way of the conventional way of localizing individual molecules, where we're trying to maximize the number of fluorescence photons, making n very large. But here it's just the opposite. So the ideal localization is when there is no fluorescence emission. And there's another implication which is quite striking. There is, in the first approximation, no dependence on the wavelengths. Why? Because what we do in this thought experiment, we match 2 points. The molecule is a point, of course, or point-like, and the zero, the central zero of the donut, is also a point. And if you match 2 points, it doesn't really matter with which wavelengths the donut has been created. So the wavelengths in first approximation doesn't play a role anymore when we find out the position of the molecule. Okay, now in reality, of course, there is no demon, but we can do, or we can build something, kind of, say, electronics, that kind of mimics the demon. And that is done. There is a controller that measures the number of detections that we get here in this confocal detector. So we have here not a camera, we have a pinhole that measures the number of detections. And of course, the more detections we have, the further out the molecule is actually from the zero of the donut. And then, of course, the brightness, as I said, will tell us how far the molecule is out actually from the position of the donut zero. And then, if the molecule, of course, starts moving, what will happen is we could try to track the molecule, so try to overlap the position of the zero with the molecule, but we won't be able to do it because we don't know where the molecule goes. We're not a demon after all. But we can measure the fluorescence that we get here at the detector, and the brightness of the fluorescence will tell us where the molecule actually is in relation to the position of the zero. So in other words, the fluorescence that we collect now is not needed to find out where the molecule is in general. It is just needed to find out where the molecule is located with respect to the position of the donut zero. And therefore, we need much fewer photons than in the previous case where we detect the position with a camera, where we localize with a camera. And so, although it won't be zero, the number of photons that we need, like in the demon case, it still will be very small. In order to explain to you what this entails, I'm showing you how this can be done in principle, this localization. So let's assume for the moment we know that the molecule is placed within this spatial interval between this purple and this orange dot. So the molecule here, the star, is somewhere in between. We don't know where it is. And the distance between the purple and the orange dot is given by L. This is the profile of the intensity of the donut, and this is the fluorescence that we get if we move the donut across the molecule. And you see what will happen. Of course, when the two coincide, the position of the donut zero coincides with the position of the molecule, fluorescence will be zero. And so you get here, in first approximation, a parabola. Why a parabola? Because the intensity here, in first approximation, intensity profile of the donut is a parabola. And this is very interesting news. So we can say that in first approximation, we have a quadratic parabolic intensity dependence here, from space, from the spatial coordinate. And this is interesting news because in this quadratic approximation, we can instantly assess that the wavelength dependence is gone. Why that? To give you a hand-waving argument, we have a simple quadratic equation that we need to solve in order to find out where the position is as a function of the fluorescence of the two endpoints. So in other words, we can measure the fluorescence n0 that is found when the donut is here. We can measure the fluorescence when the donut is here. And we don't have to scan very densely across the molecule to find out where the zero is. It's perfectly enough to measure the fluorescence at the two endpoints. We can find with a little quadratic equation solution that the position is given by xm, which is given by L divided by 1 plus square root of the ratio of the fluorescence of the two endpoints. And so with a simple equation, we can see that there is, in first approximation, no wavelength dependence. There's no wavelength dependence in here. And not only that, there's no dependence on the molecular orientation. And therefore, if we calculate now the precision we will find out something very, very interesting. So n is the number of total, say, fluorescence detections, so the sum of the fluorescence of the two endpoints. And we see now that while the precision with which you can find out the position of the molecule xm still scales with the inverse of the square root of the number of fluorescent photons, that, say, dependence still remains. We have another dependence coming in here in the equation, which is very powerful. It scales linearly with the range L in which we anticipate the molecule to be located. Now, initially, this will be the diffraction barrier, roughly. We know that the molecule is somewhere, for example, within the diffraction range. But now, once you know roughly where it is, say, within a certain range of, say, much less than the diffraction barrier, say 50 nanometers or so, then you zoom into that range and do the whole process again, measure again the fluorescence at the two endpoints, and find out where the position is. And you see what will happen. Because L is now smaller, the precision sigma will go up, meaning that sigma will become smaller and the precision more precise. So it's much more effective, actually, to reduce the region which we look for the position of the molecule than waiting for more photons to come. And this is the new feature here and the unique feature of MINFLUX, that you can bring the zero of the donut closer to the molecule, meaning that the targeted position is brought closer to the molecule, and the closer you bring the targeted position to the molecule, the fewer fluorescent photons you need to get the same precision. Or other way around, if you have the same number of fluorescence emissions, then sigma goes down, meaning the precision goes up, because L goes down. Now, in 2 dimensions, you need 3 points that you measure, or better is to use 4. So in the initial experiment, you use 4 points. And then the equation is not as simple as before, but the relationship or the dependence on the diameter L, on this uncertainty range L, still remains. It's more effective to decrease the range where you're looking for the molecule than to wait for more photons. And that means, as a rule of thumb, you need 20 to 100 times in practice fewer photons for a certain localization precision than with a camera. Why? Because the majority of the localization or the burden of photon requirement for localization is placed on the excitation beam rather than on the fluorescence emission beam. And this is the key idea here. Now, this MINFLUX localization, which is of course very effective in terms of fluorescent photons, can be used for tracking. So you can track a molecule in space, and you will be faster if you require a certain precision, because you need fewer fluorescence emissions. And this is actually shown in here, where a fluorescent protein was attached to a ribosomal subunit, was tracked, and we could get 8,000 localizations per second. And this is not really possible with a camera at the precision that we obtained here. If you want to get pictures, you have to separate the molecule. In the previous case with tracking, we had just one molecule within the focal plane or within the region of interest. If you want to take pictures, you have to separate. And this works by an on-off transition, meaning that only one molecule has to be emissive or active or capable of emitting fluorescent photons, whereas the rest has to be off, so that the signal of the two cannot be confounded. So this is the key of any super resolution method, be it STAT, STORM, PALM, whatever. You need an on-off transition. And so we can come up with a scheme that separates molecules as it is done in the single molecule localization method. So there's only one molecule within the diffraction range turned on and emissive, so to speak. And then we localize that molecule, but now, because we need fewer fluorescent photons to localize the molecule in space, we get a higher precision and therefore effectively also a higher spatial resolution. And this is demonstrated here in this scheme, where we arrange molecules in this pattern that is shown in here using a DNA or origami as a template. And now, by turning the molecules individually on and off, MINFLUX was able to resolve these molecules very, very precisely. The sigma, the precision, single standard deviation of localization was here of the order of 1 nanometer, whereas a storm under the same conditions cannot attain the higher spatial resolution, simply because the number of fluorescent detections is not enough. And also 6 nanometer in this case was also not separable with palmstone, but MINFLUX was capable of telling the molecules apart because they emitted sequentially in time, sure, but at the same time the localization precision was higher. Keep in mind, this is all done with conventional optics, so with regular objective lenses, and maybe 25 years back, 20 years back, people saw that anyone who would claim that this would be possible one day must be totally nuts, because this was absolutely unthinkable to reach a spatial resolution that is effectively at the molecular scale, so at the size of the fluorophores themselves, say a few nanometers or so. So why were we now able to reach this tremendous resolution? Simply because you need fewer detected fluorescent photons, you can localize faster because there is less drift, and there's negligible dependence on the emission dipole orientation. So the new limit is now not set by the optics. It is set by the labeling and the label size. Of course, you need to get the fluorophore close to the molecule, and don't forget, after all, in fluorescence microscopy, the only thing you can see is the fluorophore. You don't see the target molecule. No way. It's only the fluorophore that you see. And of course, one has to make sure that the fluorophore kind of represents the target molecule that you're actually interested in if you are a biologist. I'm coming back to this by showing you actually a little cartoon that I think is quite instructive. If you have, for example, a mitochondria, and you have fluorophores attached here to the inner membrane, arranged like this, would you see the crystal like that here in the fluorescent microscope? No. Even if the resolution is molecular, as it is done with MINFLUX, because fluorescence microscopy yields nothing but the fluorophores. So a perfectly resolved image that is truly perfect in terms of the optics and everything in the physics would render just these nanometer-sized dots. That's it. Don't forget that, because there's nothing more that the fluorescent microscope can do. And if you have something like molecules that are 5 nanometers apart, the resolution is 5 nanometers. But of course, you would see only the dots, only the fluorophores that are actually making up the image. So if you have many of them like that, then the image would look like this. And you won't see the crystal, of course, you will only see the molecules. This is very, very important to keep in mind. But this is not bad news in a sense. It is good news because it tells us that if you want to see molecules that are just 5 nanometers apart with a microscope that has this resolution, you can tell it apart. But ultimately, the structure, if it is very complex, of course, in order to be seen, that structure must be labeled. Otherwise, there is no way of seeing the details. Okay, so you don't see all the crystals, it's impossible, you see only the fluorophores. This is something you have to keep in mind. But this means, as I said, the limit no longer is the optical imaging, the limit is given by the labeling. Now, can you take large field of view pictures of the distribution of fluorophores? Of course, nothing else. Yes, you can. You can scan like this and then localize the molecules individually, and then you will get a picture. And this is actually shown in here with nuclear pore complexes, and the precision of each localization is on average very good. The median is 0.9 nanometers, so below 1 nanometer. It's actually sort of below the size of the fluorophore itself. A conservative estimate shows that the resolution must be, the effective resolution must be better than 3 nanometers, provided that the molecules can be switched individually. This is really important. And if they are, say, 3-4 nanometers apart, they can be separated, of course, because they emit sequentially. Now, this shows you pictures that we got after, say, turning molecules on and off individually. And then, so these little localization clouds can be associated with individual fluorophores. Of course, we don't have the ultimate proof. This is exactly one particular fluorophore, but it can be, there are arguments in terms of the labeling and the rest that you can associate with individual fluorophores. In any case, the localization precision is of the order of the size of the fluorophore itself. Compared to STED, the resolution is definitely much better by an order of magnitude, and compared to confocal, it's even 2 orders of magnitude. Again, molecular scale resolution has been reached, as I said, and the limits are set by the labeling. Is it possible to fulfill the optical conditions also in a live cell setting? The answer is yes. This has been demonstrated here. So in this case, it was a photoactivable fluorescent protein that has been used, and you see now this high spatial resolution with MINFLUX that wasn't possible to get with PALM, for example. We had collaborators that worked with PALM, but they couldn't get this with PALM at that time. So it really shows that MINFLUX is clearly superior in this case. The recording time was still on the lengthy scales, or the order of 5 to 10 minutes or so, depending on the field of view. The larger the field of view, since we have a kind of scanning method, the longer it takes. So if you go to small scales, it will be much faster. If you go to large scales, of course, large fields of view, it will be slower accordingly. But the conditions, the optical conditions, can also be maintained under live cell conditions. So 3D, yes, this is also possible. In this case, it's not just a donut in XY. There is also a structure in Z that allows us to make the localization X, Y, and Z. And so these are particular proteins from a synapse, so PSD95. And this shows that, of course, it's possible to extend this method in 3 dimensions. Now, we have used this 3D microscopy, MINFLUX microscopy, in order to address a particular biological problem in collaboration with a colleague who works very close to me here at the Planck Institute, Stefan Jacobs. And he was interested in finding out how particular proteins correlate in space. Are they colocalizing or not? And this say range of colocalization was within 20 nanometers. And you need a high spatial resolution. You need a sigma of a few nanometers in order to find out if something is closer than 10 nanometers or 5 or so, or even further away. And then he investigated mitochondrial proteins. It's part of the so-called Amigos complex. And so there's MIG10 and MIG60. And MIG19 and MIG60, and he found that MIG19 and MIG60 correlate in space, that are closer together than MIG10 and MIG60. So, MIG10 and MIG60, so he could come up with a model of how they colocalize in space and possibly interact. So for that, you need a sigma that is currently only provided in 3D with MINFLUX of the order of 3 nanometers. And also at a relatively high speed if you stay in a certain region. So this is very important. Now, I'm acknowledging the people who have contributed to this development. All of them have left my lab and now set up own labs or work in industry. And in order to disseminate this technology to many labs, the only way, in my view, to do that is to collaborate with a company that is specializing in that. And therefore, my lab collaborated with a company that was set up by my former students and myself. And they not only develop microscopes, which is, of course, that's what a company does, but also do science. And I'm strongly encouraging them to do science. It's Aberio Instruments. And so in collaboration with them, they have actually made a study and published a paper in which they showed the performance of a commercial microscope. And the good news is that even under commercial conditions and the standard lab conditions, not in a highly sophisticated conditions, you can attain the same performance as in my lab under academic, say, settings. And here what you see is again nuclear pores from in a cell. And this is a confocal recording first, deconvolved recording, and then MINFLUX is done in 3D. So the movement of the donor is done X, Y, and in Z. And one can nicely see the 2 rings, which is typical for this nuclear pore complex. The distance is of the order of 50 nanometers in Z. And this localization clouds correspond, so to speak, to molecules that are at that site. Now, if some of the spots are missing in here, it's because there was no label, most likely in the most cases. But I would like to draw the attention on the actual precision, hence resolution of the system. So this precision is 1.6 nanometers, meaning that the precision of localization in Z is extremely good, despite the fact that we have just a single lens and this kind of donut in X and Y, it's 2.2 nanometers. So it's fair to say that the resolution definitely better than, say, 4 or 5 nanometers, and depending, of course, on the number of counts that you get, it is definitely better than that. Not only you can image with a spatial resolution down to the molecular scale in 3 dimensions, you can also track individual molecules. For example, in this little experiment, what has been done is labeling a single lipid molecule and watching how it diffused in a lipid bilayer. And the numbers that you get in terms of the localization precision and localization speed are really cutting edge, like say within 230 to 40 microseconds, a precision of about 13 nanometers was attained. And so it's possible to see actually how the molecule diffuses with a high precision and at an unprecedented speed, even over a long period of time, like in this case, over 12,000 localizations. So MINFLUX is not only good for getting high spatial resolution in 3 dimensions, but also to watch or to optically detect molecular movements with the highest possible precision. A back of the envelope calculation says that with you get a nanometer precision within a 10 nanometer range. If you look for the molecule within a 10 nanometer range, within only 10 microseconds. So meaning that if you have nanometer movements taking place within 10, 20, 30 microseconds, you will be able to see that. And that, of course, opens up an entirely new field of applications that was so far possible only with some other techniques or not at all. So I think this is really a very, very exciting field of application where MINFLUX really opens up an entirely new field. And of course, the optical resolution, provided that you can switch the fluorophores on and off individually, will be on the scale of the molecules or fluorescent molecules or the labeling, say, sizes, of course, themselves, of the order 1 to 5 nanometer. Of course, depending on the fluorophore and on the sample background. Clearly, if the background gets high, then the resolution will not be as good. If the background is comparatively low, then the resolution will be down, say, to the theoretically possible numbers. But keep in mind that in terms of background, MINFLUX clearly has an advantage over camera-based techniques because it uses a confocal detector. A confocal detector is extremely good at suppressing background. This is why confocal microscopy was invented after all. Then that's the reason why you can get a molecular scale resolution in 3 dimensions, because you're not limited to turf or something, to the surface of something. You can focus into the cell and get a 3-dimensional picture, and you've seen it actually with the nuclear pore complexes. So this is why I think MINFLUX really changes the game of both super resolution fluorescence microscopy or nanoscopy and in the detection of molecular movement. And so I'm very excited to see this application being done in many labs and actually pave the way for making fundamental discoveries. So what about STAT? Now, does STAT play still a role in my lab? Well, classical STAT, well, perhaps not so much, because I'm interested in pushing the science further. But if you look at the STAT concept, you will realize that, of course, we inject a coordinate. That's the donut beam that injects a coordinate. But now it's not an excitation beam, it's a de-excitation beam. And the region where the molecule is allowed to emit is the so-called effective PSF. And outside this region, there is zero fluorescence. There is a zero fluorescence zone. So in other words, we can kind of come up with, and that's the new idea, we can kind of come up with a new concept that kind of relies on the principles of STAT microscopy, so an excitation and a STAT beam, but yet behaves like a MINFLUX system. And I'm showing you how this works. We can use this effective region in which the molecules are allowed to emit in order to mimic a donut. So we can make it move around like this, and this is actually shown now like this, and this is the little molecule. And now if you move it such that in the end, the little molecule is inside this artificially created donut, then we can locate it very effectively. Now this has been done, of course, with normal Gaussian beam by Enrico Graton and others. Well, what the difference here is that we use the STAT beam to sharpen up actually the effective region of emission, and therefore we can make this ring smaller and smaller and smaller and smaller. And this, of course, is very, very effective at finding out where the molecule is. Not only that, STAT keeps the background low. So it turned out in my lab that doing it this way with STAT is very, very effective, in part more effective than MINFLUX even. And I'm showing you this here. So the localization precision that you get with, say, a limited number of photon detections, say 100 photon or 200 photon detections, so fewer than when we had with MINFLUX, you get already precision of 2 nanometers. Why is that? Because that suppresses background. And so there is a very good contrast on the single molecule level. And some of you may say, but if you work on a single molecule basis, don't you bleach with that? No, because where the STAT beam is, there is little STAT intensity because we follow, so to speak, the molecule only, so with the center of the donut. So there's only the edge of the STAT donut faces the molecule, and the molecule doesn't bleach. So it's a strength of this concept. And therefore, we have been able to image with MINSTED, that's how we call it, fluorophores or distribution of fluorophores with very high spatial resolution. And this is a comparison now between confocal STAT and MINSTED. Becomes very obvious that resolution very high. So it's about 1200 counts, a sigma of 2.1 nanometer was reached in this sample of mitochondria, as a matter of fact. Now, another strength of this concept is that you can tune the spatial resolution actually from the diffraction limit down to the molecular scale. And this is also a unique strength among all the super resolution concepts, that you can kind of tune and select the resolution that you want. So this is something that will definitely play a role in the future, and we are very excited about this method, and there will be new developments as well. Now, so MINFLUX and MINSTED will have unique applications, in my view, when it comes to mapping molecules or fluorescent molecules and of course their target molecules ultimately in cells, provided you sort out the labeling say challenge where you need to know that the molecule actually represents the fluorescent molecule represents actually the target molecule. So molecular maps of nuclei, ER, Golgi vesicles, and so on. And then another application, which I think is very, very powerful, perhaps even unique, is to look into molecular dynamics, because I'm not aware of any localization method that can see movement of molecules within small scales so quickly and with such a high time resolution as MINFLUX. And in the future, I think also MINSTED. And with that, I thank you very much for listening so patiently. Thank you.
Thank you, Professor Hell, for the very inspiring talk and very beautiful result. Now we can join together with Professor Leigh and Professor Sauvage for the panel discussion. Hi, Alice. Now the podium is yours.
Yeah. Okay. Yeah. Very nice. Yeah. We're glad to meet you again. 3 years from your talk at Peking University. I see very nice work and a lot of new things coming in. Yeah. This time I was so lucky to have the people here, to have Peng here. Yeah. Peng, maybe you go first to ask the questions.
Oh, sure. I learned a lot from Professor Hell's talk. So first, from your slide, I saw in the MINFLUX, you can do both X, Y, and Z resolution enhancement. But why? Normally speaking, the point spread function is like a piece of rice. So the Z resolution is worse than the XY lateral resolution. But here, what I see is that it seems that the sigma of Z is even better than XY, than the lateral. Why is that?
Yeah, this is a very good question, Punk. Nice to see you again after such a long time. The answer is simple. It's because if you look at that Z-shaped donut, some people also call it bottle beam, the blobs, the intensity blobs above and below the focal plane, so the ones that are on top and below, are stronger in intensity. That means that the hole in the center is not oval. The hole in the end, if you really look into the intensity profile, looks like a sphere. And this is why the precision along the z-axis is as good as along the x and y axis. I don't know, you may remember our very, very first stat paper in 2000 that actually won a share of the Nobel Prize. If you look at that paper, it's a stat paper, not MINFLUX, of course. You will see the Z resolution is as good as the X and Y. It's because this so-called bottle beam, or this three-dimensional shape of that hole, of that donut, is such that the center is, if you look at the intensity profile, it's actually a sphere. So it's normal, it's not an artifact. This is actually what you would expect.
Wonderful. Thank you.
Okay, great. Yeah. So David, yeah, so just now you talk about, the moleculars. Yeah. So now Professor Hill's technology is looking for the moleculars. Did you have any comments or questions?
Yeah, just fantastic to see what can be done, of course, with these amazing techniques. Because going back to the talks where I followed on from Jean-Pierre, one of the reasons that we're able to be so advanced in the molecules we make is because of all the advances in instrumentation that have developed over the last few years, and seeing the amazing things that we just learned, we just saw, is just another illustration of that. It makes things so much easier in other disciplines and advances other disciplines, not just in that particular imaging methodology.
Okay,
Yes.
super. Yeah. So, okay, Martin, did you have comments?
Oh yeah, Professor Hell, that's an amazing work. It always goes on my head to look at some of the work you're doing with imaging. And for somebody who is in soft matter, I wonder, could we actually use your techniques to study diffusion in polymers and other such molecules? Because there's a non-understood aspect of diffusion, or the equation we use in chemical engineering and in chemistry are all analog based. But when you get to the level where David and JP are working, everything seems to be functional group based. So I always wonder, is diffusion actually a step-by-step process, so quote unquote quantized, or is it continuous? What is happening with diffusion? Can your method actually help us understand it?
It's a very, very, very good question. As a matter of fact, I've discussed it yesterday with my students. So this is yes, by coincidence or not coincidence. Yes, you're perfectly right. So we have approached now a range where the precision with which we can localize molecules is on the size of the molecules themselves. In fact, even smaller. So we've just published 2 weeks ago a preprint where we localized in video fluorophores down to a few angstroms. That's about a tenth of the size of the fluorophore. The fluorophore is about 2 nanometers in size, roughly. And the precision can be down to 2, 3, 4, 5 angstroms. And then, of course, you can imagine to follow that fluorophore, the movement of that fluorophore in time. And of course, it depends very much on the speed with which this fluorophore moves. If it's in a very viscous medium, so that it kind of collides with the neighboring solute, of course, then one could imagine following up that movement. So that's definitely an interesting question. I don't know if the answer is yes, if it can be seen or not, but it's definitely an interesting question. And the thing is that because we reach that localization precision, such experiments become thinkable. At least one can think about how to look into these things. And I could imagine that, or I'm actually quite confident that the methods we have developed, like MINFLUX or MINSTED for that matter, can have an impact in your field. Yes, I think so. Yes, but of course I have no proof. But say a back of the envelope assessment says yes, provided, and that's a very important thing. Provided that you have a good signal to background ratio. And fluorescence is, of course, extremely good at that. So fluorescence it provides a fantastic signal to background ratio. As we all know, you can see or detect single molecules with a very, very, very good background. So we need that. We need to be precise in the positioning. We need a very good signal to background ratio as it is provided by fluorescence. If you cannot live with that, if you cannot provide that, it's not going to work.
Maybe Alice, sorry, I'm going to hog a few more minutes.
Sure.
In relation to what you just mentioned, we have been struggling with the question of self-assembled monolayers and trying to understand how they organize on the surface. They're so small that we cannot see them. So maybe as you discuss with your student, there might be an opportunity there in self-assembled systems where we see an influence of a single carbon orientation, but we don't know how the domains affect that. So I'll shoot you an email and you can.
Yeah, okay, thank you. So I'm not sure whether we can go there, but I wouldn't promise that this would work, you know, but as I'm saying now, the realm of molecular scale, of genuine, of true molecular scale is now accessible with far field optics, with lenses, you know. And this was kind of weird. I mean, even 5 years or 6 years back, even at the time the Nobel Prize was given in 2014, no one would have really dared saying that at some point we'll be able to kind of say address quantitatively a nanometer or 2 or 3 or so. That was not possible even in 2014. But now it has become possible. So the field has progressed since then.
Very good. Thank you.
Okay, Peng, I think we have a question from audience. Did you have it?
Me?
Yeah.
I can't see it. I mean.
Okay. Yeah. Okay. Maybe let me read it. Okay.
Please read
Yeah.
it.
Yeah. We have questions from the audience, you know, on the chat box. This was from 3 Peanuts. Okay. Yeah. From each molecular, there will be about, you know, 100,000 photons generated before blurred. If you imagine under 1000 pfs speed, there are lots of duplications of one switching event. How did you avoid it? Or did you use this localization into final localizations? I hope I read it.
Okay, I don't know if I understood the question correctly. So the question was, so usually there are many detected photons, and how do you convert this into a single localization? So usually in a normal localization, you need maybe 10,000 photons to have one localization, and only few fluorescent molecules yield more photons than that. Usually they bleach away or they go to a dark state where they stay for such a long time that you won't get them until before the time they recover. Since we can localize with much fewer molecules, we can afford, so to speak, stopping the localization process after about 1,000, 2,000, 3,000 photons. Then, of course, it's possible to localize again the same molecule. Then usually, since this happens one after the next, it is associated very closely to the first localization. But usually for MINFLUX and MINSTED, we don't go for such molecules. We select other molecules that people have not used before that give fewer photons out, but have a very, very silent dark state. So what is important for MINFLUX and also MINSTED is that the dark state doesn't emit. There is no emission in the dark state. There is no, say, transient fluctuation from the dark to the bright state or something for a short period of time. But it's a very good on-off contrast ratio, put it that way, with a limited numbers of photon emissions. So we put a lot of effort. I should say the real chemists in my lab, I mean the organic synthetic chemists, they design fluorophores that are just for the purpose of these new concepts. And so we have fluorophores in the pipeline. Some of them have been published that are just optimized for getting the best possible, highest spatial resolution without any ambiguity. This is work in progress, but we have come a long way already, and there will be more published soon.
Okay, so Peng,
I have some questions as well. Stefan, as we can see, you have pushed the 200 nanometer limit of the diffraction limit down to 20 nanometers from STED and from the resolved technique. And then today it demonstrated that you can further push it down to 2 nanometers or even 1 nanometer resolution. So the 1 nanometer resolution is already very close to the size of the molecule. I was curious, what's your next goal toward that?
Yeah, it's a good question, because yes, the localization precision is down to the size of the molecule, and the resolution is then limited just by the ability to distinguish two molecules that are very close. I mean, you have to have them on and off. What comes next? In a way, you are right. I mean, the physical conceptual limits more or less have been reached. So it's a fact. I mean, you are basically down to the scale of the fluorophores themselves. Of course, there is a benefit in finding the position of a molecule with very high precision, especially if you want to do some sort of, I hesitantly call it structural biology. Let's assume that you have a fluorophore close to a certain part of a protein, yeah? And then you want to know what is the protein, how is the protein oriented in space? And then by having the fluorophore attached to a certain region, you can learn something about the orientation of the protein or a conformational change or something like that. And then, of course, the precision with which you localize the fluorophore really matters. Then it matters that you have a precision of 2 angstrom or 3 angstrom or whatever, yeah? And so there are new type of applications that are coming up that draw actually on this very high localization precision. So I see the field going into a direction where users may take advantage of this high localization precision. But from the pure resolution viewpoint, so if you just look at it from a pure physical optics viewpoint, I agree with you that the limits have been reached in terms of resolution, because the smallest entity that you resolve in a fluorescent microscope is the fluorophore itself. As I said, the fluorescent microscope sees nothing but a fluorophore, which is just fluorophore, nothing else. And the smallest entity is the fluorescent molecule. And of course, there is no better resolution than resolution that resolves two fluorophores that are at molecular distance. I mean, it's clear. I mean, it's the currency of fluorescence microscopy, the unit currency. I mean, that's the fluorophore. And once you reach that resolution, then you're done. And reaching that resolution was all but trivial, as you certainly appreciate. Say 20, 30 years back, it was considered totally crazy, insane, even to think about it was considered insane. And now it is absolutely rock solid. So the physics behind it, or physical chemistry, whatever you like to call it, is rock solid.
Okay, I also have one other question, which is, I was already fascinated at like 10 years, now more than 10 years ago, about the concept of STED microscopy. And now you invented the MINFLUX. And in your talk, you also talked about this little demon. So I was curious, how do you come up with this really mind-blowing concept? How do you invent those ideas? Can you give us some patterns so that the students can follow you?
Punk, I wish I knew myself. I don't know, perhaps because I like it. I really like the field. And I mean, as you know, I've always been fascinated with this idea of getting the resolution up to the highest possible level. And it was kind of, to be honest with you, it was kind of my how should I say, it's my life story in a way. And I've started the field. I think it's fair to say that before me, there was no one who really thought about doing it seriously with a light focusing microscope, with objective lenses, not with near field optics as people tried, but with light microscope. And I was convinced that the key to getting the resolution is the fluorophore and the transitions within the fluorophore. And so this is something that I kind of lived for academically, at least. And so I wanted to push it to the end, and the Nobel Prize was just, okay, it was something, yeah, it was a big accolade, no doubt, but it was not a goal. So I was still in love with this idea of really getting it to the highest possible resolution level. And arguably, if you are in love with something, then things come very naturally.
Yes, love the science that you are doing. Yeah, this I believe this is the key. And I see there are two questions from the audience. The first one is, what is the MINFLUX disadvantage compared with storm, such as speed or imaging depth or something else?
Yeah, so far, the way it has been implemented so far, it's not possible to generalize things because of different concepts. The way it has been implemented so far, when it comes to making large fields of view, it is slower for sure. Because so far it has been implemented with a donut, meaning that you have to reach basically every molecule that you want to image with the donut. And then, of course, the recording time scales with the area or with the volume. It's very simple. So in the current implementations, when you are happy to look into protein complexes or small fields of view with a very high spatial resolution, clearly the MINFLUX is superior to any storm, PAN, whatever, very clear. And it's also superior in terms of background. Why? Because it has a confocal detector. That's also important. And then in terms of depth, that's very, very important point. You can go deeper. Why? Because the background suppression is done by a confocal pinhole. There's another advantage of MINFLUX over PAN. Since it's imaging with a point, with a donut, the total, say, load, the illumination load, yeah, or photo damage, if you want to call it like this, is lower. Why? Because you look only at a single point. If you do a palm or storm, you illuminate a large area at once, and if you create a radical, there's no escape for that radical. So in that sense, it's also more benign to the cell that you look at or to the sample that you look at. The downside, as I said, is that if they have large fields of view, it takes longer. That's for sure. Yeah.
Okay, great. And I see another question from the audience. So although the center of the donut beam is totally dark, there will be no photo damage in this region. However, the other region of the donut is still shine light onto the specimen. So still there is photo flux there, and the possible photo damage can happen. Is that true?
Yes, of course. Whenever you have light, there is a potential for the damage, but keep in mind the brightness of the donut, okay, of the excitation donut in MINFLUX is of the same order of that on confocal. And so it's not very bright. So one should not be confused with the idea that donut is always very bright. I'm not saying that. So we have powers of the order of 50 microwatts or so, 60 microwatts, 70 microwatts. And not only that, since the donut has a slightly larger area than the confocal spot, the intensity is lower. So the nonlinear photo damage is also lower. Moreover, as I said, since it's only the donut area that is illuminated, the other parts of the sample are not illuminated. So the total photo damage, so to speak, or the photon load is much lower than in palm or storm. That's something one has to keep in mind. But when it comes to photo bleaching, it's a good point. Keep in mind, the fluorophore, the active fluorophore, is just in the center of the donut. On the other side, on the outside, the fluorophores are not active. They are in a protected state. They are in a dark state in which they do not absorb. And so they are not photo bleached. This is a major difference also to, say, to STED or to a normal confocal microscope. So the fact that you have an on-off switch and there is a protected there's a protection, say, transition at the donut crest, so to speak, that keeps the fluorophore, so to speak, in a benign situation. So they are not photo damagers. So the fluorophore sees only the intensity that is at the donut center. That's why we are so sensitive when it comes to localizing individual molecules.
Great.
Okay.
Well,
yeah. Great. Paul, did you also have questions? Or we got
one final question.
Okay.
Can I?
Please.
Yes. Yeah. I see that Abira is commercializing or instrumenting, helping the scientists all over the world. So if for a Chinese biologist, if they want to access to this fascinating technology, MINFLUX, where can we get it?
Actually, you have to ask this question to the company, you know.
Okay.
I think I'm not the right person to ask. But there are very, very capable Chinese scientists who are very active in China. Leigh Xiaoyu is one person I know very well. He's very active, and I think Abira also hired a new application scientist for Beijing. And so there will be increased activity in China, and there will be opportunities for Chinese scientists to try it out. I'm very confident. Actually, there is, to my knowledge, there is a system in Shanghai by Professor Gu Min. And I think there is also in another place a system or a system that is in the process of being shipped. So there is opportunities for trying it out and come up with your own conclusion about the versatility and usefulness.
Yeah, I heard that the University of Science and Technology in China is installing the second one.
I see, right. Yeah. Yes, so I'm very pleased. And so what I can say, I know that there's about 12 systems so in the world, in various places, and the feedback has been very, very positive. So I get very, very good feedback, and people have data. And yesterday, I listened to a presentation given by a scientist from Switzerland, and he surprised me by showing actually MINFLUX data. I didn't know that he had even access to MINFLUX, and said, look, what great results we have here. And I found this actually quite nice, because it gives me, of course, some pleasure to see that biologists make good use of it and find out new things.
Okay, great. Yeah. Actually, we see our next speaker, Professor Lihong Wang, is here. Hi, Professor Wang. Did you want to say hello to everyone?
Hi.
Yeah, hello, Stefan. Hello, everybody else.
Hi.
Yeah. Okay, thank you. Yeah, we catch a time. Yeah, very productive, panel discussions, and thank you everyone for joining this. Yeah, we will move to our next talk. I hope to see you. Stefan, hope see you in Peking next time. Yeah. Okay. Yeah. So yeah, let me introduce Professor Lihong Wang, our next speaker. Yeah, actually, we are really proud of Professor Lihong Wang because he is alumni from Huazhong University of Science and Technology. Yeah, and I see that this time, this event also we were part of the 70th anniversary of this university. I was alumni too. So Professor Lihong Wang was graduate from HUST and then go to US, got his PhD, and then he done super, great jobs, and not only in one university. Now he's a professor in Caltech. I visited his lab was 2 or 3 years ago. Oh my God, he has the biggest lab in Caltech and very, very productive. So Lihong, I don't take all of your time. Please go ahead to share your slides, and we got to your story.
Great. Can you see my slides?
Yes. Beautiful.
Thank you, Professor Zhang, for the very kind introduction. It's always hard to follow Stefan's talk, so I'll do my best. This year is the 70th anniversary of HUST, which I'm very proud of as an alumnus. I'm grateful for receiving rigorous first-rate training in the major of laser. Zhu Jiusi was the then president of the university. he actually believed at the time that math and English were most important. In our first semester, we took only those two subjects as our main courses. I now realize how visionary he was. Please allow me to dedicate this presentation to my alma mater. Today, I'll talk about photoacoustic tomography for deep penetration in biological tissue and compressed ultrafast photography for speed. Why optical imaging? First of all, we can provide molecular specificity. From the physics perspective, we know that light-matter interaction takes place at the molecular level. This is a very unique position. If you look at the entire EM spectrum, light occupies this tiny region, but this is the only region of the spectrum that allows us to provide molecular specificity. Given the fundamental role of molecules in biomedicine, we really have to work on this problem, given all the challenges we have. By detecting molecules, we can provide in vivo functional imaging, analogous to functional MRI, in vivo metabolic imaging, similar to PET, in vivo molecular imaging of gene expressions or disease markers. Now, even in vivo label-free histologic imaging of cancer without tissue excision. But we face daunting challenges because turbidity is ubiquitous. You look around the world, every material is essentially turbid, maybe to different extent. Even water and air are turbid to some extent. If you look at biological tissues, with the exception of our eye, all other tissue types are extremely turbid. This simulation here shows how photons propagate. Within the first millimeter or so, photons propagate as a group, but beyond which you will see a diffusion process, very similar to dye diffusion or heat diffusion, which presents a big challenge for light penetration in scattered biological tissue. Let's look at the history of optical imaging. More than 350 years ago, conventional microscopy was invented, which allows us to provide fantastic spatial resolution, but the penetration was limited to about 100 microns, which is something we call the aberration limit, correlated with one mean-free path in biological tissue. We stagnated at this limit for hundreds of years until modern light sources were invented. By using the coherence properties of light, modern light sources, we can provide confocal to photon optical coherence tomography, which broke through the aberration limit and advanced the penetration by order of magnitude and reaching the so-called optical diffusion limit, which correlates with one transfer mean-free path. Using photoacoustic tomography, we advanced the penetration depth by nearly two more orders of magnitude. Now we're talking about multiple centimeters of penetration in biological tissue, providing human organ level imaging or whole body small animal imaging. Of course, we do face the next challenge, which is something we call the optical dissipation limit. Which technology can overcome the next challenge is still an unknown question. The ultimate goal is to reach something closer to the absorption limit, which can be quite deep using if you were to use the right laser wavelength. Photoacoustics as a physical phenomenon is well known for over 100 years. It was first reported by Alexander Graham Bell. He had this idea of photophone instead of telephone. He encoded sound into a sunbeam. The light beam was propagated. At the remote end, the light can be converted into sound using the photoacoustic effect. Of course, Bell had no access to laser, ultrasonics, tomography, and computer. Using this set of modern concepts, we combine with this pretty old physics, photoacoustics, to achieve a novel imaging technology, photoacoustic tomography. In photoacoustic CT, we expand a short laser pulse such that energy per area is within the safety limit. So this is extremely safe to use. We allow photons to wander around to scatter in biological tissue to provide deep penetration. But when photons are absorbed, we generate rapid heating. Every millidegree of temperature rise gives us a detectable pressure, 800 pascals of pressure. In fact, modern detectors is actually much more sensitive than 800 pascals by orders of magnitude. Within the NC safety limit, you can heat up tissue to hundreds of milledegrees. So this allows us to have good signal to noise ratio to provide fast imaging. Then we detect ultrasound emitted from the tissue. Because ultrasound scattering is orders of magnitude weaker than optical scattering, we can form a very sharp image based on the ultrasonic signal, based on the wave and the time of arrival information. However, the contrast is from light absorption. We're combining light absorption contrast for molecular information and acoustic resolution for deep penetration in a single modality. We do have to use something called inverse spherical redound transform to form an image. Without getting into the detailed math, let me use an analogy to explain how this technology works. If you want to pinpoint a single sound source, you can use triangulation. Let's say you have lightning, thunder. When you see the lightning, you can start your clock at time 0. When you hear the thunder, you can record a time delay T1. Multiplying T1 by the speed of sound will give you a radius for a spherical shell on which lightning took place. If you have 3 such measurements, you can triangulate the sound source. Now, of course, in biological tissue, we have a volumetric sound source instead of a single point source. We want to figure out the exact distribution within the sound source. So 3 detectors won't be sufficient. In reality, we have to use hundreds, even thousands of detectors to form a sharp image. In 2003, we achieved the first functional, also the first in vivo, photoacoustic tomographic images in small animals with intact scalp and skull. By wiggling one side of the whiskers, the contralateral side of the brain was activated. Using photoacoustics, we can see this activation non-invasively. This paper has become one of the most cited papers in our field. In fact, after the publication of this paper, our field has experienced exponential growth. Since 2010, the Conference on Photoacoustics has become the largest at the 20,000 attendee Photonics West. Now it's the largest by far. Since a few years ago, our field has started publishing over 1,000 peer-reviewed papers every year. Now you do observe this pandemic dip, hopefully we can pull out of very soon. This technology has been commercialized by a number of companies. Our lab is associated with a few of them. It's also notable that Seno Medical has received FDA approval last year for human breast imaging. So this technology is very widely available for both small animal imaging and human imaging now. Fast forward to 2017, we finally realized single impulse panoramic photoacoustic CT. For the 2003 work, we used a single element transducer. We had to rotate around the small animal to form image, which took 20 minutes. With this single impulse version, within tens of microseconds, we can acquire an image. The system can be configured for truncal imaging. We start with the laser. We route the laser beam to a conical lens to form a hollow cone beam for maximum energy delivery efficiency. We use a full ring ultrasonic transducer to form a panometric view of the cross-section. This allows us to minimize motion artifacts or to minimize subsampling artifacts. We use Nyquist sampling to minimize any subsampling artifact. We use preamplifiers to maximize signal-to-noise ratio. We use one-to-one data acquisition for maximum speed. Within the acoustic transit time across the field of view, which is tens of microseconds for a small animal, we can acquire data for a cross-sectional image. Then we use a computer to reconstruct the image and present the data. Here's a close-up. A hollow cone beam illuminates the tissue to generate photoacoustic waves. We use an ultrasonically focused array to receive the acoustic wave. Of course, we run the inverse read-on transform to form a 2D cross-sectional image. And the ultrasonic focus gives us elevational or Z resolution. The system can be configured for brain imaging as well. We use a diffuser to form a solid as opposed to a hollow cone beam. And for brain imaging, this is more efficient. Then the rest of the system operation is the same as that for truncal imaging. This is a demonstration for truncal imaging. The red line shows the current cross-section being imaged. You can see the image right here. The red box shows the close-up. Each image, again, was acquired within tens of microseconds. Then we repeat our laser pulse at 50 hertz. That means we can provide 50 hertz frame rate. We get 50 frames per second. And you can see the detailed structures within the whole body of a small animal without injecting any contrast agents. So this technology can be used for all sorts of biological studies, including drug discovery. In standard drug discovery study, they may have to use X-ray, but because you want to monitor the same animal over a long period of time, you have to repeat imaging. Radiation dose becomes a concern. Sometimes the animal dies actually before you finish the experiment. With our technology, you don't have such a problem because everything is very safe. Now, our technology has been licensed to a company called Calpact. They've perfected the technology. They've generated better images than our initial work. As you can see right here, this is a slight courtesy of Professor Leigh. He was able to see deposition of protein in renal cortex, part of the kidney. So this is a form of molecular imaging. Now, as soon as we completed our animal study, we were so excited about this work, we said, well, we need to scale up the system for human level imaging. And this is our system, something we call single breath hold panoramic photoacoustic CT for human breast imaging. We have to scale up the system to accommodate most breasts. The initial design was 22 centimeters in diameter, which allowed us to accommodate most breasts with a slight deformation against the chest wall. Most breasts can be compressed without pain, without causing any pain, to about 4 centimeters in thickness. This allows us to minimize the requirement for light penetration. The rest of the system design is very similar to the small animal system. We use 1064 nanometer laser light for maximum tissue penetration. This system operates at this point, allows us to achieve multiple centimeters of penetration, hundreds of microns resolution. This plot shows the imaging depth versus the spatial resolution. Each horizontal bar represents one particular implementation of this technology. So photoacoustic tomography is highly scalable across vast length scales from organelles to cells, tissues, all the way to human organs or small animal organisms. This might be a very unique capability because by detecting the same contrast, the same optical absorption contrast, we can cover a vast length scale of biological interest. And this might provide a capability for multi-scale biological studies of a given problem, be it cancer or brain disorder. And that allows us to get to the fundamental problems of a given disease. And photoacoustic tomography can also connect with standard medical imaging, actually CT, ultrasound, MRI, and PET. I'll give you some examples later on because we use ultrasound transducers for detection, where standard ultrasound imaging use ultrasound transducers for both transmission and detection. So we can share the same set of ultrasound transducers. Automatically, our images can be co-registered. And we share some similar contrast mechanisms with MRI, and we can also co-label, to share the same contrast with PET. And you can see the synergy. And so photoacoustics, because of this multi-scale imaging capability, we can serve as a central glue to connect with all the other modalities to provide a comprehensive view of a given problem. This is one of the first images we acquired from a healthy human volunteer. We use color to encode depth. You can see the nipple region, and a single 2D image was acquired with a single laser shot. The data was acquired within 150 microseconds. For a 3D image of the entire breast, we asked the patient to hold her breath within a single breath hold, 15 seconds, which can be also condensed to 10 seconds for certain patients. We can form a 3D image. The smallest blood vessel diameters we've imaged was 1/4 millimeter. And this is far smaller than what MRI can do. Now, standard MRI imaging requires injection of heavy metal contrast agent, gadolinium, and we don't have to inject any contrast agent. So we have human volunteers coming to our lab. They said, well, we don't want to expose ourselves to MR contrast agents so frequently. And so they want to use a non-invasive technique that requires no contrast agent injection to image their breasts. We can provide 4 centimeter penetration as demonstrated by the slice images here. Of course, the goal is to provide tumor imaging. This is an example where we imaged a radiographically dense human breast. Even at the age of 69, this patient had dense breast, which was not able to be imaged with X-ray mammography properly. So X-ray mammography missed the tumor. Ultrasound actually picked up the tumor. We labeled the tumor region with this metal target. Then we took a second mammogram. And you can see the dark target right here. Using photoacoustic tomography, we can see the tumor very clearly, as indicated by the double arrow. And we can analyze the blood vessel density. You can see a very high contrast. Because we can image so fast, we can track the motion of blood vessels, which allowed us to analyze the motion and figure out the strain. The strain map shows that the tumor region is much stiffer than the surrounding normal region. So we provide dual contrasts, even with a single laser wavelength already. It allows us to provide more accurate diagnosis. Again, because the imaging rate is so high, we can monitor motion of blood vessels in real time. And by analyzing the motion of vessels, for example, in those 2 pixels, we can see the vastly different magnitude of the motion. And the stronger motion indicates arteries because we have heart-induced pulsatile motion, where veins, as we know, has much smoother blood flow, so it has a smaller magnitude of oscillation. Therefore, we can color code arteries and veins. This is of physiological interest. Then we want to develop our technique to the next generation. We use twice as many ultrasound detection channels. We want to provide both anatomical imaging and functional imaging. Anatomical imaging takes 10 seconds for a 3D image, but for functional imaging, it takes only 2 seconds for a 3D image. And so this system is useful for both breast and brain. This is a layout for brain imaging. We use 2 different laser wavelengths. And at 1064, the signal is dominated by oxyhemoglobin. At 694, the signal is dominated by deoxyhemoglobin. Both are important because the combination of them will indicate how our body delivers oxygen. And we have this hemispherical detection geometry. We have arcs of ultrasound transducers. By rotating the arcs, we can cover the entire hemispherical surface. This is an example of human breast imaging. You can see isotropically, with isotropic spatial resolution, detail maps of blood vessels. We can look at projection images here as well. This slide shows the first functional photoacoustic tomographic images of human brain. By doing finger tapping, we can see brain activation. And this is a special group of patients where their skull was temporarily removed for medical purposes. We call them hemicraniectomy patients. So we can convincingly see finger tapping brain reaction. On the next slide, I'll let our surgical collaborator to narrate the technology.
Here we present results from subject 1, 7T MRI.
Please let me know if you
left,
don't hear the
functional
narration.
packed on the right. Individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. Vessels for co-registration are then labeled 1 through 4, vessel 1 and 2 being superficial temporal artery, 3 and 4 being cortical arteries. The images are overlaid, and then individual functions are flashed in, starting with finger tapping, lip puckering, tongue tapping, passive listening, and silent word generation. The vessels are again pointed out individually, vessel 1 and 2 being branches of the superficial temporal artery, 3 and 4 being cortical vessels. The lateral perturbations allow for visual spatial appreciation of the co-registration. The images are then separated, and native T1 masks are faded in. Again, 7T MRI on the left, functional packed on the right. Individual functions are then flashed in, starting with finger tapping, axial, and coronal images through the area of interest are introduced below. Next, lip puckering, tongue tapping, passive listening, and silent word generation.
Now, as you might know, 7 Tesla MRI represents the strongest magnetic field FDA approved for clinical use. And so we're comparing with the state-of-the-art MRI. In fact, within the entire Los Angeles area, there's only one 7 Tesla MRI because it's extremely expensive. So why do we want to develop another technique for functional brain imaging? We already have both MRI. In comparison to functional MRI, photoacoustic tomography provides richer contrast, faster response, lower background, higher linearity, greater portability, open platform, lower acoustic noise, much lower cost, and magnet-free environment. And so, as you know, this 7T MRI costs $10 million to buy, more than $100,000 per year to maintain. This is just so expensive, it's not widely accessible. We can provide a much cheaper system for brain imaging and with some other benefits as well. And also the magnet provides a challenge for certain surgical tools. Now the initial test was in a special patient group without the skull. The next goal is to implement trans-implant version of our technology. So after the patient had a acrylic implant, we can still see the brain function as demonstrated right here using finger tapping. Of course, the ultimate goal is to image normal subjects. And in this particular study, we provide transcranial functional photoacoustic imaging of human brains. And for this particular patient, he has both sides. One was open without the skull, the other one is normal. And we imaged both sides. You can see brain functions occurring at both places through finger tapping. So this has become extremely exciting. Of course, we like to do more studies. The other exciting aspect is, where is the physiological limit of technology? You know, hypothetically, we can improve the signal to noise ratio, we can improve the sensitivity. What's the ultimate response time we can provide? And so far, for both MRI and functional photoacoustic CT, we're talking about multiple seconds before we can capture the functional response. But the physiological limit can be studied in a small animal. We actually found out using a single impulse stimulated fast initial depth in capillary level imaging, we found less than 1 second response time. And so here we have a 40 millisecond impulse response, and we can detect oxygen saturation response within 130 milliseconds. Using total hemoglobin concentration, we have a response time 3 times as long, but still less than 1 second. So this study defines the ultimate physiological limit we should aim at for our in vivo human study. Because photoacoustic tomography can be scaled across a vast range of lengths, and now we want to show you some of the microscopic work. This photograph shows the first 3D photoacoustic microscope. This close-up gives us the key component. We use a donut beam to illuminate the tissue. The core of the beam was made dark to minimize surface interference. We use confocal detection. The ultrasound focus is aligned with their optical focus to maximize the signal to noise ratio. With a single laser impulse, we can get a 1D depth resolved image by detecting the time of arrival of the photoacoustic signal. This whole system can be, this assembly can be scanned in this water tray to get a 3D image. Through this membrane window, we couple light and sound. The tissue is placed below the membrane window. This system operates at this point. We just moved somewhere around here to here so that we can provide multiple millimeters of penetration, tens of microns in resolution. This is a demonstration of an image of our own palm without injecting any contrast agent. Again, we can form a very sharp image of blood vessels. Using X-ray, you have to inject heavy metal again, typically iodine-based contrast agent. Again, here we don't. We use blood as our endogenous contrast. You can look at the B-scan images to see the standard skin structures. As we know that primary cancer doesn't necessarily kill the patient. It's the metastasis that kills the patients. And so metastasis is really the danger here for cancer management. But there's no non-invasive technique that allows us to image circulating tumor cells or CTCs. Using photoacoustic tomography, we want to detect CTCs in vivo. And we want to even detect the entire volume of blood in a human. We have roughly 5 liters of blood. And so this is a start. We started with imaging of melanoma CTCs because melanoma CTCs tend to have a higher concentration of melanin. That gives us very high contrast. By tuning the laser wavelength, we can see melanin far better than any other components in the blood. And so melanin containing particles just jump out in our images. You can see this particle flowing across the field of view. We can capture several times. And here you see a twin or doublet flowing across our field of view. We can see them multiple times. So this is very, very convincing that we are seeing melanin containing particles. And this provides a non-invasive technique for maybe screening, detection, diagnosis, prognosis, monitoring of therapy. So this has vast potential applications. We can advance the penetration, advance the image resolution even further to a single-digit micron level at expense of penetration. So this is an example where we can see single red blood cells. We can watch in vivo how they bifurcate. We can image human level single red blood cells. And in fact, we can monitor the oxygen saturation of hemoglobin. Using pseudo color, we can see how a single red blood cell, if you look at right here, we can see how the color varies. So as oxygen is released from a single red blood cell, and the oxygen level will change. And so this provides a tool for fundamental studies at the lowest level, single cell level, how oxygen is delivered in our body. We all know that physicians have two eyes, essentially radiology and pathology, so to speak. Radiology is non-invasive, but pathology is invasive. We have to cut tissue. We have to go through a number of steps before we can view the images. Now, can we do better using photoacoustics? In fact, we can provide label-free histologic imaging, right? Directly labeling or by directly imaging DNAs and RNAs in cell nuclei. And this is an example where we image a piece of human breast tissue using photoacoustics without labeling or staining. We can differentiate normal from human breast tumor. We validated our images using standard HE stained images. You can see how well they correlate. They're almost exactly 1-to-1. In fact, our pathologists can make diagnosis using our images already. This is a more recent example where we provide decalcification-free and label-free photoacoustic histology of bone specimens. Again, we're imaging cell nuclei by exciting DNAs and RNAs. The left side shows photoacoustic microscopy images without decalcification. We can acquire the image within 11 minutes, where standard pathology would take up to 7 days because you have to go through a lengthier process to decalcify the bone specimens. And we use artificial intelligence to pseudo-color our images. Now pathologists can read our images as if they were reading the standard HE stained images. So you can see the immediate potential impact of this in the clinic application. We can advance the penetration or advance the resolution even further for organelle level imaging. This is an example. Using high NA, we can achieve diffraction limited resolution at 234 nanometers, and we're imaging mitochondria. Using nonlinear photoacoustics, we can provide super resolution imaging at nanoscopic level, and we're providing 90 nanometer resolution. Not quite as high as Dr. Hell's 1 nanometer resolution, but you can see the advance here already. You can compare the two images. You can see how well we can see the internal structure of mitochondria. Here's a EM micrograph for comparison. Now let me transition into high-speed imaging. We're providing the fastest imaging for real-time imaging of even a light pulse. So photoacoustic tomography focuses on the depth side of imaging. CUP, compressed ultrafast tomography or photography, focuses on the time axis. Before this technology, there was no technology that was fast enough to image a light pulse in real time in 3D space. And so we developed this version at 100 billion frames per second frame rate. With this frame rate, with a single laser pulse without repetition, we can see the pulse propagation in space, how the light pulse is reflected, refracted. Here, we have 2 light pulses having a rays in 2 different materials. We can also provide a single shot fluorescence imaging. And we changed our system into two colored. So the red channel detects the excitation light. The green channel provides imaging of the excitation light pulse, and the red channel provides imaging of the fluorescent light. And many of you have heard of FLIM, fluorescence lifetime imaging microscopy, which requires some sort of scanning, so it takes some time to build up an image. But here we can image with a single shot in real time. And so this fluorescence decay takes only nanosecond scale, but it feels like eternity because we're imaging so fast. And so we have picosecond time resolution. And the videos have been slowed down by 10 billion times. So you're watching the slowest slow motion movies right now. How does this technology work? Let's start with the object with the intensity I versus X, Y, and time T. We route the intensity to this digital micromirror device, which has a pseudo-random number code. Let's call that C versus XY. These are ones and zeros. So 1 means on, 0 means off. And the encoded light is routed to this street camera. Unlike the standard operation of a street camera, which uses a very narrow slit, we open up the slit as widely as possible. We convert photons into electrons through the photoelectric effect. And then the electrons are pulled in vacuum toward the back end. When the electrons goes through this pair of electrodes, we apply a voltage ramp. So there's this shearing effect or ramping effect. Depending on the time of arrival of the electrons, they will experience different levels of deflection, very much like how an oscilloscope works. So that allows us to freeze time. In other words, later on, we can use a slow camera to capture the deflection angle, and we can convert the deflection angle into time, which provides very high temporal resolution. The electrons are converted back into photons, then we can use a CCD camera to capture the distribution. In the end, we can mathematically describe the entire physical process. E represents the CCD reading versus XY, and we have intensity I to begin with from the object, which goes through the operator C, which is encoding, shearing S right here, and temporal integration due to the exposure time of the CCD. All we have to do is to invert this matrix. However, we got a problem. So I is three-dimensional, E is two-dimensional. In general, you have far more unknowns than you have measurements. That means you cannot invert this matrix directly. However, intensity I is usually sparse. So using compressed sensing concept, we can actually invert this matrix and form an image. There are many potential applications. We can image superluminal Mach cone related to Cherenkov radiation. And so NASA captured this image when object was flying supersonically. You can see this supersonic Mach cone or sonic boom. But using light, we build an artificial superluminal situation. We have this tunnel, which is air filled within a medium. And so light pulse travels faster in the tunnel than in the medium. That's called superluminal propagation. And that creates this cone structure with a single light pulse without repetition of the light pulse at all. You can capture this cone structure for the first time. As we know, phase contrast microscopy has played an important role. It allows us to see contrast where entity contrast is not available. You can provide label-free imaging of cells. And so here we incorporated phase contrast mechanism into cup. We provide phase contrast cup. Here is a shock wave for demonstration. Now you can imagine there are some applications in biomedicine where you can probably see fast events in cells using this technology. Chaos is of great interest, not only in physics, but also in biology. For example, heartbeat irregularity is related to chaos. Fetal hypoxia can be modeled using chaos as well. And here we demonstrate optical chaos at light speed. And so we build this half mushroom chaotic cavity. And so we launch a light pulse. In fact, we captured 2 takes. You can see take 1 and take 2. By eyeballing the pulse propagation, we don't see much difference. So we overlaid the 2 takes. At the beginning, the 2 light pulses are well aligned. You can see that they're together, but with time, they will start to split. So this is a signature of chaos. We can also study the transition from a stable cavity to a chaotic cavity using a curve gate. This is a light speed switch. It turns on and off. We start with this rectangular box, which is a stable cavity. You see the light pulse will travel periodically. And then we turn on the gate to transition to this chaotic cavity. Now you can study the chaos. And so this provides a tool that allows us to study in real time because chaos is not easily repeatable. And CUP, single shot CUP, provides a perfect tool for that kind of study. This is a plot showing the sequence depth, namely the number of frames per movie versus the imaging speed. CUP is in the preferred corner, so provides the highest speed in real-time imaging and the largest sequence depth. And there are multiple versions within the CUP family as well. And so far, we've demonstrated 70 trillion frames per second. And that's not even the ultimate limit. Now, of course, you can also slow down CUP to cover the entire space. So the shearing rate is highly adjustable. So just because we put the technology here, but it doesn't mean we cannot cover the lower rate. If you have a given problem that requires a lower rate, then we can adjust the frame rate accordingly. CUP is just a tool. It can be coupled with a microscope or a telescope. So you can study microscopic phenomena. You can also study astrophysics, for outer space phenomena. So you can imagine this is just like a camera, except this is very, very fast. With that, let me conclude. I'm really grateful to Caltech for providing me a dream lab. This photograph shows one of the floors of our lab. We have multi-scale imaging, nanoscopic at the proximal end. We have human scale imaging at the distal end. We have openings for graduate students and postdocs. We welcome students and postdocs from all related disciplines, physics, optics, mechanics, ultrasound, you name it, or even biology and chemistry. Credit goes to my lab members. They've been working extremely hard. We have funding primarily from NIH, but some from NSF. We have a couple of books. If you're interested in more details, you're welcome to read them. Thank you very much.
Thank you, Lihong. Amazing talk. Actually, I remember one Chinese word is the most, super kungfu is the fastest one. So you done it, right? Yeah. So yeah, now we got on the stage for our panel discussion. I think Peng, yeah. So you here? Yeah. So
yes. Professor Wang, it's indeed very, very beautiful work, and it's really amazing. So my first question is, I see that you have demonstrated the photoacoustic pathologic histology imaging in the but without fixation, without biopsy. So I was curious why the DNA and RNA is sensitive to the light. What wavelengths are you using in that work?
So thank you, Peng. So we actually tune the wavelengths to a UV region where DNA and RNA are very, very absorbing. So we use 266 nanometer wavelengths. So it's also a widely available wavelength. You basically use second harmonic generation twice, right? You start from neodymium YAG laser, you get to that wavelength. So you can actually see some other components as well, but DNA and RNAs are much more absorbing than other components. In fact, later on, I don't have time to show, you can use that to provide multi-contrast imaging. You can see other proteins, and you can even see blood cells and neurons as well. And we can get a 3D image of the entire mouse brain, for example. That's of interest to neuroscience people.
I see. With the 266 nanometer conventional objective does not transmit that wavelength, right?
That's right. Yeah, that's right. You have to use a UV compatible system.
I see.
Very good question. Yeah. Yeah, in fact, the entire system, the entire light transmission system has to be UV compatible. Yeah.
Okay, cool.
It's
Hi,
really
Stefan.
powerful.
Yeah. Hi, Dr. Hell.
Yeah, it was very impressive, I must say. I was very pleased to see those data, especially in the context you've shown. And I think it's really cutting edge science. Lihong, I was wondering, I mean, being interested on a small scale, what is actually the detection limit that you have, say, in terms of the signal that you get when you really go to very small scales? Because, I mean, in principle, I mean, fluorophores, they give off light, but they give also off acoustics, of course.
That's right.
And of course, the bad fluorophores, they give off just acoustics. I mean, just sound that we don't hear, but you can make it hearable, so to speak, by appropriate detection. And people have been trying that. So, but where do you see the serious limits? So why? I fully understand that your direction is more interesting. It's very clear. But if you go to the very small scale, and you alluded to that with the mitochondria and so on, what are the real limits that you see now, or do you see a potential in that field?
Yeah. So this is a great question. So I don't think our field has pushed in your direction as hard as we should have. So we pushed to 90 nanometer resolution. Then the postdoc found a great job. So we got a new person, right, working on that. And, we're revisiting that direction again. So we like to push it further. In terms of sensitivity, we push it down to a single nanoparticle. That's already demonstrated reliably. For a single organic molecule, nobody has demonstrated. So we need probably to get hundreds of molecules to get enough sensitivity at the moment. Right. But it doesn't mean this is the ultimate limit, because sensors are getting far more sensitive. We started with what's available to the ultrasound community. They worry about both transmission and detection. And so they use piezoelectric transducers. Now the photoacoustic community has switched to optical sensing of pressure. Light can sense pressure even at a greater sensitivity, by orders of magnitude greater. And so there's a hope one day that we can push to a single molecule level for acoustic detection. And then we're talking about more like something similar to STED and MINFLUX.
Right.
Yeah. And so there's hope for that, because it's not a fundamental limit. It's more like a technological limit.
That's right.
Yeah.
I mean, history has shown that if something is not fundamental, but technological, technology will evolve to a level where it will be possible in the end.
Yes. Yeah. And so even with the piezoelectric transducer, we're talking about millidegree or even sub-millidegree type of sensitivity. And now imagine with optical sensing, people use micro ring resonators, use Faber-Pro sensors, and you can elevate that sensitivity by another order of magnitude or even more. And then ultimately we can reach that goal for a single molecule detection. Then we can probably borrow some of the concepts, from your current field, hopefully, and see how far we can push.
Okay, there may be potential collaborations. Here will question from the audience. He says that Professor Wang, you mentioned a lot of advantage for the F-PET. Can it replace the fMRI in the future?
So, I mean, if you go to radiology, you'll see a number of imaging modalities. It's never like one technology would totally replace the other technology. They're all complementary. And that's why you can name, starting from X-ray, ultrasound, MRI, PET, SPECT, you name it, right? So, and now photoacoustics. And so the reason that they're complementary is that MRI is still a very universal tool that for whole body imaging. And for photoacoustics, we can provide human organ level imaging, but we're not at a whole body level yet, you know. And so we can provide, for example, for a human breast, one-way penetration is 4 centimeters. And people have demonstrated that if you provide light illumination to both sides, you can essentially double that thickness. So you're talking about 8 centimeters, but that's still not quite the whole body length. And so people are trying to work using, you know, all sorts of techniques. For example, you know, wavefront shaping, you know, can we actually overcome the scattering problem so we can provide even deeper penetration than the 4 centimeter one-way penetration? One day we may get there, but that technology is facing daunting challenges because to correct a wavefront, you got to measure the phase, and the spectral pattern actually decorrelates quite fast in biological tissue, you know, milliseconds or even microsecond scale. So we got to do everything extremely fast within the spectral correlation time. So that's not mature enough for real human use yet. So in the meantime, we are also providing or developing microwave-induced photoacoustics, because as we know, MRI is basically based on RF, right? At the right frequency of RF, you can provide whole body penetration, yet you're providing microwave contrast. And so the microwave or RF version of photoacoustic tomography can potentially provide whole body imaging, you know, without the side effects of some like X-ray or other type of problems. So hopefully one day we'll find even broader applications in the clinic.
Okay, that's super. Yeah, another question from Stola. It says that brilliant work. Consider light scattering, maybe limited application of our PAM. Are there any good methods to improve this problem? One possible solution may be wavefront shaping. However, it's too time consuming, right?
Yeah, so great question, right? So you actually predicted my answer already, right? I guess you asked a question before I answered the previous question. You can see that you're talking about the optical resolution version of photoacoustic microscopy. You know, photoacoustic can be scaled, right? The original purpose of developing photoacoustic tomography was to overcome the scattering problem by tolerating the scattering problem, right? So we allow photons to scatter because all photons are good photons. You know, in standard confocal or two photon version, you try to reject the scattered photons, right? Like OCT as well. And, you know, OCT through coherence gating, you reject scattered photons. So you use the ballistic photons to form a sharp image. But in photoacoustics, in general, we tolerate scattering. Because any photons, when they're absorbed, even after scattering, they provide useful information because the spatial information comes 100% from the acoustic detection side. The excitation side does not provide spatial resolution. Then we said, once we developed the acoustic resolution photoacoustic microscopy, we said, well, why don't we also come back to the top 1 millimeter, you know, within the ballistic regime, we can provide optical resolution because the optical wavelength is shorter than the acoustic wavelengths. You know, the acoustic wavelengths can also be shortened, but however, you pay a price. To shorten the acoustic wavelengths, you have to use a higher frequency ultrasound. The higher frequency ultrasound has limited penetration. And so for a usable 1 millimeter penetration, you can only use maybe up to 100 megahertz ultrasound. So your acoustic wavelength is still longer than optical wavelengths. And that's why we developed optical resolution PAM, photoacoustic microscopy. Now you're in the same boat as the standard ballistic imaging like OCT or confocal or two photon, right? So because you are trying to use the ballistic photons and you try to reject the scattered photons. So unless you do something you mentioned, wavefront shaping, because the hope is that through wavefront shaping, you can focus deeper. This has been demonstrated in ex vivo situation very beautifully by multiple labs. And so especially if you have a guide star, our lab developed ultrasound encoded guide star. This is the only, in fact, non-invasive guide star inside the tissue. We can use a light to encode coherent light. We can use ultrasound to encode coherent light. At ultrasound focus, you basically have a guide star. You know, since you know where the ultrasound focus is, and so you can actually focus to the ultrasound point. And this allows us to provide much deeper optical focusing ability than the ballistic regime. And so that's a direction. But the problem is what I just said in the previous answer. We're fighting against speckle decorrelation. So everything has to be done within the speckle correlation time. Also, ironically, the correlation time depends on the depth as well. So the deeper you want to image, the faster the speckle decorrelation. And so that means you will face greater and greater challenges as you aim at a greater depth. I hope that answers your question. It's a great direction, but not mature enough for practical applications yet.
Okay, 3 peanuts come back again. I'll ask another question. One question is to you. How did you think about comparing the recent developed interference, FNIR, for brain activity recording, which is much cheaper and compact, advantage and disadvantage over FNIR?
Okay, so FNIRs is a great technology. It doesn't use ultrasound, so it's just light goes into our brain. You detect the backscattered or diffusely scattered light coming out of the brain as well. So it's usually, one of my colleagues, Joe Culver, is a pioneer in this field. He probably has published one of the most exciting papers in the field. So if you talk to him, he was my friend and colleague at the same university. He would tell you that FNIRs has 2 pixels in the depth direction. And so the resolution is very poor. So don't expect a sharp image. Don't expect very good localization at all using FNIRs. And this problem is quite fundamental. When I joined the field 30 years ago, right? So DOT, diffuse optic tomography, was the hottest topic at the time. At the time, we had hope that we can overcome all the practical problems and get resolution like X-ray, right? So really fine resolution, or at least MRI type of millimeter scale resolution in human breast or brain. But that turned out to be false. So it turned out the limitation is quite fundamental, as Dr. Hell and I were talking about, right? Some limitations are practical, technology-based. Some limitations are quite fundamental. So it turned out this DOT problem is quite a fundamental issue. You can study how ill-posed this problem is. This inverse problem is very ill-posed by looking at this near field problem, how quickly the signal decays. You can look at the equation we solved is essentially the same as heat diffusion. So it's a diffusion equation. The diffusion process is chaotic. The entropy just goes up. So it's very hard to invert that problem and form a very sharp image. And so without getting into the details, you'll find out, the current limit is 2 to 3 pixels. And when I teach this class, I teach optical imaging. One of the chapters is on DOT. We ask students to analyze this. You can also read Joe Culver's paper. You can analyze using SVD, singular value analysis. You can find the fundamental limit of this technology. And so you're talking about maybe 2 to 3 pixels in the depth direction. In the XY direction, you have similar resolution, but you can use a larger field of view. So we don't talk about the number of pixels you have in the XY direction, but the depth direction shows the most fundamental limit. So if you want to image 2 centimeters deep, you're talking about roughly 1 centimeter spatial resolution. Where with photoacoustics, with MRI, we're talking about millimeter scale resolution.
Okay, great. So any further questions, Dr. Hell? No? Okay, Peng?
No.
Okay, that's super. Yeah.
Thank you all. Great to see you all here online.
Sure.
Great panel. Yeah, thank you all of you. Yeah. Okay. Yeah. So I will send gift to you. I hope can meet you face to face, but this time it's too hard. I hope in near future. Okay.
One day,
I can meet all of you again. Okay. Thank you very much.
Great.
Yeah.
Great. Thank you all.
Yeah.
Thank you.
Okay.
Bye-bye.
Okay.
Yeah.
Thank you. Bye.
Let me conclude this session. So tomorrow we also have one more day. Yeah. Our schedule tomorrow will be okay. Let me hold on it. So, okay, tomorrow we will have Professor Gang Chen, to get on the stage, and another professor from Fudan University. Yeah, so in the evening, so we also continue this great talk. Okay, thank you, and bye-bye.
Bye-bye.